The edge of everything. Imagine standing at the absolute boundary of existence itself. Not at the edge of space, not at the end of time, but at the precipice where reality itself begins and ends. This is not a physical place you could travel to with any spacecraft, no matter how advanced. This is something far stranger, far more profound, and infinitely more unsettling. This is the edge of everything we know, everything we can know, and perhaps everything that can ever be known. We call it the Big Bang. That moment roughly 13.8 billion years ago when our universe exploded into existence from an infinitesimally small point of infinite density and temperature. But here is where things become truly bizarre. When we ask what came before that moment, we are not simply asking about ancient history. We are asking a question that threatens to unravel the very fabric of logic itself. Scientists tell us that time itself began with the Big Bang. Space expanded from that primordial point. The laws of physics, as we understand them, came into being in those first fractions of a second. So asking what came before the Big Bang is like asking what is north of the North Pole. The question seems to dissolve into meaninglessness because there was no before. There was no earlier. There was nothing. But human minds are not built to accept nothing. We are pattern-seeking creatures who live in a universe of cause and effect. Everything we have ever experienced has a cause. Every effect has a prior condition. The coffee cup falls because you knocked it. You knocked it because you reached for your phone. You reached for your phone because it buzzed. Each moment flows from the previous moment in an unbroken chain of causation stretching back through your entire life, through all of human history, through the entire history of Earth, through the formation of our solar system, through the birth and death of previous generations of stars. And then we hit a wall at the Big Bang, where this chain of causation simply stops. Or does it? This is not just an academic question for theoretical physicists to ponder in their ivory towers. This is a question that strikes at the heart of what it means to exist at all. Why is there something rather than nothing? Why does this universe exist? Why these laws of physics and not others? Why this particular arrangement of matter and energy that allows stars to form, planets to coalesce, life to emerge, and consciousness to arise to ask these very questions? The standard Big Bang theory is one of the greatest intellectual achievements in human history. It brings together observations from astronomy, predictions from Einstein's general relativity, evidence from particle physics, and the cosmic microwave background radiation that fills all of space. The evidence is overwhelming. The universe was once incredibly hot and dense, and it has been expanding and cooling ever since. We can trace this expansion backwards in time with remarkable precision. But precision has its limits, and those limits appear at the very moment we want to understand most. As we rewind the cosmic clock backwards, temperatures rise, densities increase, and eventually we reach a point where our equations break down completely. This is not because our mathematics is insufficient or our measurements are imprecise. This is a fundamental breakdown in our understanding of reality itself. At the Planck time, approximately 10 to the power of negative 43 seconds after the Big Bang, quantum effects become so strong that space and time themselves lose their meaning. Imagine trying to measure the length of a ruler that is vibrating so violently it becomes a blur. Now imagine that ruler is space itself, and the vibrations are quantum fluctuations so intense that the very concepts of here and there, now and then, cease to have any definite meaning. This is where physics encounters its ultimate crisis.
We have two great theories that describe reality. General relativity explains gravity, the large-scale structure of space-time, the motion of planets and galaxies, and the expansion of the universe itself. Quantum mechanics explains the behavior of atoms, subatomic particles, light, and all the forces of nature except gravity. These two theories are spectacularly successful in their respective domains. General relativity has been confirmed by every test we can devise, from the precession of Mercury's orbit to the detection of gravitational waves. Quantum mechanics is the most precisely tested theory in the history of science, with predictions confirmed to 10 decimal places. But these two theories are fundamentally incompatible. They describe reality in completely different, mutually contradictory ways. General relativity treats spacetime as a smooth, continuous fabric that can be warped and curved by matter and energy. Quantum mechanics insists that everything in nature is fundamentally discrete, quantized, and inherently uncertain. When we try to apply both theories simultaneously at the extreme conditions near the Big Bang, we get nonsensical answers. Infinities appear in our equations. Probabilities become greater than 100%. The mathematics simply explodes. This is not a small technical problem that physicists will solve with a few more years of research. This is a sign that we are missing something fundamental about the nature of reality. And that missing piece might be the key to understanding what, if anything, came before the Big Bang. Some scientists argue that the question itself is meaningless. If time began with the Big Bang, then there is no before. The universe is simply all of space and all of time, and asking what came before time is like asking what color is the number 7. It is a category error, a confusion of concepts that don't actually apply. But other scientists are not satisfied with this answer. They point out that our current theories break down at the Big Bang, which means we cannot trust what those theories tell us about whether time truly began or not. Perhaps time did exist in some form before the Big Bang. Perhaps our universe emerged from some prior state of existence that we have yet to understand. And this is where things become truly fascinating, because in the last few decades, physicists have developed multiple competing theories about what might have preceded the Big Bang. These are not wild speculations or science fiction fantasies. These are serious scientific hypotheses grounded in mathematics and theoretical physics that make predictions we might someday be able to test. Some theories suggest our universe is just one bubble in an eternally inflating cosmic foam, where new universes are constantly being born from quantum fluctuations. Others propose that the Big Bang was not a beginning but a transition, a bounce from a previous universe that collapsed down before expanding outward again. Still others argue that our three-dimensional universe might be a holographic projection from a two-dimensional surface, or that what we call the Big Bang was actually the collision of higher dimensional membranes in a space we cannot directly perceive. Each of these theories is strange, counterintuitive, and challenges our everyday notions of reality. But then again, so does quantum mechanics. and quantum mechanics is undeniably true. The universe is under no obligation to make sense to human intuition. Reality operates according to its own rules, and those rules are often bizarre beyond imagination. What makes this moment in scientific history so exciting is that we are not just philosophizing about these questions. We are gathering data. The cosmic microwave background radiation, the afterglow of the Big Bang itself, contains patterns and fluctuations that carry information about the very earliest moments of cosmic history. Gravitational wave detectors might someday pick up signals from before the Big Bang, if such signals exist and can propagate through the Big Bang itself. Particle accelerators probe energies closer and closer to those present in the first instance of the universe. We live in an age where the ultimate questions about existence are becoming experimental questions, where the boundary between physics and metaphysics is blurring and shifting, where what seemed forever beyond human knowledge might actually be within our grasp. But even as we gather more data and refine our theories, we must confront an uncomfortable possibility. Perhaps there are limits to what we can ever know. Perhaps the nature of reality before the Big Bang, or the reason the universe exists at all, lies fundamentally beyond the reach of scientific inquiry. Not because we lack the technology or the intelligence, but because the universe itself prevents us from accessing that information. This would be a profound and somewhat melancholy conclusion. We are creatures who evolved in the last few 100,000 years on a small planet orbiting an ordinary star in an unremarkable galaxy. Our brains were shaped by evolution to help us survive on the African savanna, not to comprehend the ultimate nature of reality. It would be remarkably fortunate if the universe happened to be comprehensible to beings like us, all the way down to its deepest foundations. Yet we keep trying, because that is what humans do. We ask questions. We seek answers. We push against the boundaries of knowledge, and sometimes, just sometimes, those boundaries give way. What seemed impossible becomes possible. What seemed unknowable becomes known. The Big Bang should not have been discoverable. By all rights, the origin of the universe should have remained forever in the realm of myth and speculation. Yet through careful observation, mathematical reasoning, and inspired leaps of insight, we have reconstructed the history of the cosmos back to its first seconds. We have discovered that the universe is expanding, that it was once incredibly hot and dense, that the light from that primordial fireball still fills all of space. If we could discover all that, what else might we discover? What other boundaries might we cross? What other seemingly impossible questions might we answer? The universe that shouldn't exist does exist. We are part of it. We are made of atoms forged in the nuclear furnaces of stars that lived and died before our sun was born. We are the universe becoming aware of itself, looking back across billions of years to witness its own origin, and daring to ask what came before that origin. This is the story of that quest, a journey to the edge of everything, and perhaps beyond, when time didn't exist. Close your eyes and try to imagine a moment without time. Not a frozen moment, because freezing implies time stopped. Not an eternal moment, because eternity is still a concept that requires time. Try to imagine genuine, timelessness, where the very concept of before and after has no meaning whatsoever. You cannot do it. Your mind will not let you. Every thought you have unfolds in time. Every memory is of something that happened before now. Every plan is for something that will happen after now. Your entire conscious experience is built on the scaffolding of time, on the flow from past through present into future. Asking you to imagine timelessness is like asking a fish to imagine what it would be like if water didn't exist. Time is so fundamental to consciousness itself that we cannot step outside of it even in our imagination. Yet this is exactly what physicists claim happened, or rather didn't happen, before the Big Bang. Time itself did not exist. Not that time was frozen or suspended or moving slowly. Time simply was not a feature of reality at all.
And if this is true, if time genuinely began with the Big Bang, then the entire question of what came before becomes not just unanswerable, but actually meaningless. To understand why this is so philosophically radical, we need to understand what time actually is. And that turns out to be one of the most difficult questions in all of physics. In our everyday experience, time seems simple enough. It flows forward at a steady rate. 1 second follows another in an unbreakable chain. We age, seasons change, civilizations rise and fall, all carried along by the river of time, flowing inexorably from past to future. Time seems as real and tangible as space itself. More so even, because while we can move freely through space, we can only move through time in one direction, at one speed. But physics paints a very different picture. According to Einstein's theory of relativity, time is not separate from space. They are woven together into a single fabric called space-time. And this space-time can be warped, stretched, and twisted by matter and energy. Time does not flow at the same rate everywhere. It moves slower in strong gravitational fields. It moves slower for objects traveling at high speeds. Two observers moving relative to each other will disagree about whether two events happened simultaneously, or one before the other. This is not a theoretical abstraction. This is measured reality. GPS satellites have to account for the fact that time moves slightly faster in orbit than on Earth's surface, or your navigation would be off by miles. Particles in accelerators experience time dilation that allows them to travel much farther than they should before decaying. Astronauts on the International Space Station age slightly slower than people on the ground. Time, in other words, is not the fixed, absolute backdrop that our intuition suggests. It is malleable, relative, and intimately connected to the structure of space and the distribution of matter and energy. This is already strange enough, but it gets stranger still when we try to understand what time is at the most fundamental level. Some physicists argue that time is an emergent phenomenon, something that arises from more fundamental processes, but is not itself fundamental. Just as temperature emerges from the motion of countless atoms, but is not a property of individual atoms, perhaps time emerges from some deeper level of reality where it does not exist at all. In this view, time is an illusion, or at least, a very high-level description of something more basic. Other physicists insist that time is real and fundamental, woven into the deepest structure of physical law. The equations that describe quantum mechanics, for instance,
treat time very differently than they treat space. Time is a parameter that tells you how the system evolves. Space is something the system exists within. This asymmetry suggests that time might be truly fundamental, after all. The debate remains unresolved, and it matters enormously for understanding the Big Bang. If time is emergent, then perhaps it makes sense to talk about a state of reality where time had not yet emerged, where the universe existed in some timeless quantum state. But if time is fundamental and cannot be separated from existence itself, then asking what existed before time is truly nonsensical. Let us explore what physics actually tells us about time near the Big Bang. As we rewind cosmic history, strange things start to happen to the nature of time itself. In the early universe, when temperatures and densities were enormous, quantum effects become increasingly important. And quantum mechanics has a very peculiar relationship with time. In classical physics, time is deterministic. If you know the exact state of a system now, and you know the laws of physics, you can predict its state at any future time and retrodict its state at any past time with perfect accuracy. Time is like a railroad track stretching in both directions. And once you know where you are on the track, you know everything about where you have been and where you are going. Quantum mechanics shatters this picture. In the quantum realm, the future is not determined by the present. Instead, there are multiple possible futures, each with a certain probability. A particle does not have a definite position until you measure it. It exists in a superposition of many possible positions simultaneously. Only when you observe it does it collapse into one definite state. This is not because of our ignorance or because our measurements are imperfect. This is the fundamental nature of reality at the quantum level. The future is genuinely open, genuinely indeterminate, genuinely probabilistic. And if the very early universe was governed by quantum mechanics, as it surely was, then time itself becomes fuzzy and uncertain near the Big Bang. Imagine trying to define what happened at exactly 10 to the power of negative 43 seconds after the Big Bang. At this scale, the Planck scale, quantum fluctuations in space-time itself become significant. The smooth flow of time breaks down into a kind of quantum foam, where past, present, and future lose their distinct identities. Cause and effect become blurred. The very notion of a sequence of events stops making sense. Some physicists describe this using the concept of imaginary time. In ordinary mathematics, we distinguish between real numbers and imaginary numbers. Real numbers are the familiar counting numbers and fractions that we use every day. Imaginary numbers involve the square root of -1, which seems like meaningless nonsense, but turns out to be incredibly useful in mathematics and physics. Stephen Hawking and James Hartle proposed that near the Big Bang, time might have an imaginary component. In their model, as you go back toward the Big Bang, time gradually transforms from real time into imaginary time.
And in imaginary time, the distinction between time and space disappears. All 4 dimensions become spatial. There is no flow, no before and after, just a kind of eternal geometry. In this picture, asking what happened before the Big Bang is like asking what is south of the South Pole. The question assumes there is a direction to go, but actually you have reached a boundary where that direction stops having meaning. The universe does not have an edge in time any more than Earth's surface has an edge in space. You can travel as far south as you want, but eventually you reach the South Pole, and then you are traveling north no matter which direction you go.
Similarly, you can trace time backwards as far as you want, but eventually you reach the Big Bang, and there simply is no further back to go. This is an elegant solution to the problem of the beginning. It avoids the paradox of something coming from nothing by suggesting that the universe has no beginning, just as a sphere has no edge. The Big Bang is not a moment in time, but rather a boundary condition, the point where time transitions from imaginary to real, from spatial to temporal. But not everyone finds this solution satisfying. Critics point out that imaginary time is a mathematical trick, not necessarily a description of physical reality. Just because the equations work does not mean the universe actually operates this way. And even if it does, we are still left with the question of why this particular mathematical structure exists rather than some other structure or no structure at all. Moreover, there are other ways to think about time near the Big Bang that lead to very different conclusions. Some approaches to quantum gravity suggest that time might be fundamentally discrete rather than continuous. Instead of flowing smoothly, time might tick forward in tiny, indivisible chunks, quantum moments separated by Planck scale intervals.
In this picture, there would be a first moment of time, a genuine beginning, though perhaps that beginning emerged from some prior timeless state. Other theories propose that time is an illusion created by the growth of entropy, the tendency of systems to become more disordered. We perceive time flowing forward because entropy increases in that direction. The past is low entropy, organized and orderly. The future is high entropy, disorganized and chaotic. Our memories form in the direction of increasing entropy, which is why we remember the past but not the future. But if this is true, then what happens near the Big Bang when entropy was at its minimum? Some physicists speculate that on the other side of the Big Bang, entropy might increase in the opposite direction, creating a mirror image universe where time flows backwards relative to our own. From the perspective of inhabitants of that universe, they would be moving forward in time away from the Big Bang, just as we are. But relative to us, their time would be running in reverse. This is not just wild speculation. It falls out naturally from certain cosmological models and from attempts to explain why entropy was so low at the Big Bang in the first place. If the universe is symmetric in time, with entropy increasing away from the Big Bang in both temporal directions, then the low entropy at the Big Bang is less mysterious. It is simply the midpoint, the moment of maximum order. Imagine a video of a breaking glass. You can easily tell if the video is playing forward or backward because entropy increases when the glass breaks. The intact glass is low entropy. The scattered shards are high entropy. Time seems to have a direction, but now imagine a video that shows only the single moment when the glass is perfectly balanced on the edge of a table, neither fallen nor safe. That moment looks the same played forward or backward. It has no inherent temporal direction.
Perhaps the Big Bang is like that moment of perfect balance. Not a beginning, but a point of symmetry. And on either side of it, time flows in opposite directions, both moving away from that central point toward higher entropy futures. These ideas are speculative, but they are grounded in serious physics and mathematics. They represent genuine attempts to grapple with the deep mystery of time itself and what it means for time to begin or not begin. And they all share a common thread.
They all suggest that our intuitive understanding of time is deeply inadequate for understanding the earliest moments of cosmic history. We think of time as a flowing river carrying us from past to future. But physics suggests time is more like a dimension of space-time that can be warped, quantized, reversed, or even transmuted into space itself. We think of the Big Bang as the beginning of time, but physics suggests it might be a transition point, a boundary condition, a moment of symmetry, or even an illusion created by our limited perspective. What makes all of this more than just abstract philosophizing is that these different views of time make different predictions about the structure and history of the universe. They predict different patterns in the cosmic microwave background radiation. They predict different behaviors for gravitational waves from the early universe. They predict different outcomes for high-energy particle collisions. In principle, we can test these ideas. In practice, the tests are extraordinarily difficult because they require probing energy scales and time scales that are far beyond our current technology. But the fact that they are testable at all, even in principle, means we are doing science here, not just philosophy. And that brings us back to the central paradox. If time began with the Big Bang, then there was no before, no prior cause, no previous state, nothing. But if time did not begin with the Big Bang, if it extends back in some form beyond that moment, then we need to understand what existed in that prior time and what caused the transition to our current universe. Either answer seems impossible. Either something came from nothing, which violates everything we know about causation and conservation laws, or something existed before the Big Bang, which seems to contradict the very meaning of the Big Bang as the beginning of everything. This is the paradox at the heart of cosmology. This is why the universe should not exist, and this is why physicists keep searching for new theories, new mathematics, new ways of thinking about time and existence that might resolve this seemingly unresolvable contradiction. The answer, if there is one, will almost certainly be strange beyond our ability to visualize or comprehend intuitively. But that has never stopped us before. We have already accepted that time is relative, that particles are waves, that empty space seethes with energy, and that the universe is expanding into nothingness. We have learned to accept the unacceptable, to believe the unbelievable, because observation and mathematics compel us to. Whatever the truth about time before the Big Bang, it will surely be equally strange, equally counterintuitive, and equally true. The quantum foam. Picture the calmest ocean you have ever seen. A mirror-smooth surface stretching to the horizon, perfectly still, reflecting the sky with flawless clarity. Now imagine diving beneath that surface. As you descend, you notice something strange. The water is not calm at all. It churns and roils with currents invisible from above. Deeper still, you find vortices and eddies, swirling patterns of flow that appear and disappear in fractions of a second. And if you could somehow magnify your vision to see individual water molecules, you would find absolute chaos. Molecules bouncing off each other millions of times per second in completely random directions, a seething frenzy of motion that somehow, when averaged over trillions of particles, appears as perfect stillness. This is a metaphor for the quantum foam,
the bizarre substrate of reality itself that might hold the key to understanding what came before the Big Bang. What appears smooth and continuous at large scales becomes increasingly turbulent as we zoom in, until at the smallest scales, everything dissolves into a probabilistic froth of uncertainty, where the very fabric of space-time itself fluctuates wildly in and out of existence. The quantum foam is not just a poetic name. It is a serious prediction that emerges from attempting to apply quantum mechanics to space-time itself. And if this prediction is correct, it means that reality at its deepest level is nothing like what we experience in our everyday lives. It means that the solid, stable, predictable world we inhabit is merely an illusion created by averaging over countless quantum fluctuations occurring at scales far too small for us to perceive. To understand the quantum foam, we first need to understand the quantum vacuum. Most people think of a vacuum as empty space, a region containing nothing at all. But quantum mechanics insists there is no such thing as truly empty space, even in a perfect vacuum, with no particles, no radiation, no matter or energy of any kind. Something is still happening. The quantum vacuum seethes with activity. This activity comes from a fundamental principle of quantum mechanics called the Heisenberg uncertainty principle. This principle states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This is not a limitation of measurement technology. It is a fundamental feature of reality itself.
Particles genuinely do not have both a definite position and a definite momentum simultaneously. But the uncertainty principle applies to more than just position and momentum. It also applies to energy and time. The more precisely you specify when something happens, the less precisely you can specify how much energy is involved. And this has a shocking consequence. For very brief moments, the uncertainty in energy can be enormous. Energy can seemingly appear out of nothing, violate the sacred law of conservation of energy, as long as it disappears again quickly enough that the violation is within the bounds of quantum uncertainty. This is not speculation. This actually happens. The quantum vacuum continuously produces pairs of virtual particles that pop into existence, exist for a fleeting instant, and then annihilate each other and disappear. An electron and a positron materialize from nothing, exist for a time so brief it makes a nanosecond seem like an eternity, and then recombine and vanish. This happens everywhere, all the time, throughout all of space. We know this is real because these virtual particles have measurable effects. They alter the energy levels of atoms in ways we can detect with extraordinary precision. They create a tiny force between metal plates placed close together in a vacuum, called the Casimir effect, which has been measured in laboratories. They even contribute to the anomalous magnetic moment of the electron, one of the most precisely measured quantities in all of physics, with theory and experiment agreeing to 10 decimal places. The quantum vacuum is not empty. It is full of potential, seething with evanescent particles that flicker in and out of existence like foam on the surface of a breaking wave. And this is just particles. When we try to apply the same quantum principles to space-time itself, things become far stranger. Einstein taught us that space-time is not a fixed stage on which events play out. It is a dynamic entity, that can be warped and curved by matter and energy. Massive objects like stars and black holes create dips and valleys in the fabric of space-time. The Earth orbits the Sun not because some force reaches across space to pull it, but because the Sun's mass warps space-time, and Earth simply follows the straightest possible path through that curved geometry. But if space-time is a physical entity that can be warped, then it should also be subject to quantum uncertainty. Just as the electromagnetic field fluctuates at the quantum level, creating virtual photons, and just as matter fields fluctuate, creating virtual particles, space-time itself should fluctuate at the quantum level. The smooth geometry we experience should give way, at small enough scales, to a churning quantum foam, where the very notions of distance and duration lose their meaning. John Wheeler, one of the great physicists of the 20th century, coined the term quantum foam to describe this state. He imagined that at the Planck scale, about 10 to the power of -35 meters, space-time would resemble a foam or froth. At this scale, quantum fluctuations in the geometry of space-time become so large that space and time themselves become uncertain. Wormholes might spontaneously form and dissolve. Tiny black holes might pop into existence and evaporate. The smooth fabric of space-time might tear and reconnect in a constant frenzy of topological chaos. This is far beyond anything we can directly observe. The Planck scale is unimaginably small. An atom is to the Planck length as the observable universe is to a human hair. We have no technology even remotely capable of probing such tiny distances, but we can calculate what should happen there, using the principles of quantum mechanics and general relativity, and those calculations point unmistakably toward quantum foam.
The problem is that when we actually try to do these calculations rigorously, we run into severe difficulties. Quantum mechanics and general relativity, our two great theories of nature, refuse to play nicely together. When we try to quantize gravity, to apply quantum principles to the gravitational field and the geometry of spacetime, we get nonsensical infinities in our equations. The mathematics breaks down completely. This is the famous problem of quantum gravity. Despite decades of effort by some of the brightest minds in physics, we still do not have a consistent, complete theory that successfully merges quantum mechanics with general relativity. We have several promising approaches: string theory, loop quantum gravity, causal set theory, and others, but none has been definitively confirmed by experiment, and they all make different predictions about the nature of the quantum foam. Yet despite this uncertainty, almost all physicists agree that something like quantum foam must exist. The logic is simply too compelling. Spacetime is physical. Quantum mechanics applies to all physical things. Therefore, spacetime must exhibit quantum behavior. The alternative would require us to believe that spacetime is somehow exempt from quantum mechanics, which would be even more strange, and would raise the question of why such an exemption exists. And this brings us back to the Big Bang and the question of what came before. If spacetime itself is subject to quantum fluctuations, then perhaps the Big Bang was itself a quantum fluctuation. Perhaps our entire universe, with its 100 billion galaxies, each containing hundreds of billions of stars, emerged from a quantum fluctuation in some prior state of the quantum foam. This idea seems absurd at first. Quantum fluctuations are tiny and fleeting. Virtual particles exist for infinitesimal fractions of a second before disappearing. How could something as vast and long-lived as our universe possibly be a quantum fluctuation?
The answer lies in a concept called quantum tunneling. In classical physics, if a ball does not have enough energy to roll over a hill, it cannot get to the other side. It will roll back down. But in quantum mechanics, there is always a tiny probability that the ball can tunnel through the hill, appearing on the other side without ever having been on top of the hill. The higher and wider the barrier, the less probable the tunneling, but it is never completely impossible. Now imagine that instead of a ball and a hill, we are talking about the entire universe and the energy barrier between non-existence and existence. In classical terms, a universe cannot spontaneously appear because it would violate conservation of energy. The universe has positive mass energy, and you cannot create positive energy from nothing. But in quantum terms, there is a tiny but non-zero probability that the universe could tunnel from non-existence into existence. Moreover, due to the peculiar properties of gravity, the total energy of a gravitationally bound system can be negative. The gravitational potential energy is negative and can cancel out the positive mass energy. Some calculations suggest that the total energy of the universe might actually be zero, with positive mass energy exactly balanced by negative gravitational energy. If this is true, then the universe could appear as a quantum fluctuation without violating energy conservation at all. Zero energy transforms into zero energy, with the zero distributed between positive and negative contributions. This is the idea of a universe from nothing, championed by physicists like Alexander Vilenkin and others. The universe does not need a cause or a prior state. It simply quantum tunneled into existence from the quantum foam, from a state of no space, no time, no matter, no energy.
The probability of this happening is extraordinarily small, but in an infinite quantum foam with infinite opportunities for fluctuations, even extraordinarily improbable events will eventually occur. There is something deeply appealing about this idea. It would mean the universe is truly self-contained, requiring nothing outside itself to explain its existence. It would resolve the paradox of the first cause. It would answer the question of what came before the Big Bang by saying that nothing came before, that the universe and time itself emerged spontaneously from timeless quantum indeterminacy. But there are serious challenges to this picture. For one thing, we do not actually have a complete theory of quantum gravity, so we cannot calculate reliably what happens in the quantum foam at Planck scale energies. We are making educated guesses based on extrapolating theories that work at lower energies, but we cannot be certain those extrapolations are valid. For another thing, even if a universe can quantum tunnel into existence, we need to explain why our particular universe exists, rather than one of the infinite other possibilities. The quantum foam could presumably fluctuate into universes with different laws of physics, different numbers of dimensions, different fundamental constants. Why did we get this universe? With these laws, these constants, these initial conditions. Some physicists respond by appealing to the anthropic principle. If the quantum foam is constantly producing universes with random properties, then most of those universes will be sterile and lifeless. Only universes with very special properties will be capable of producing stars, planets, chemistry, and eventually life. We observe this universe because we could not exist in any other kind. Our existence selects, from the vast ensemble of possible universes, only those capable of producing observers. This explanation makes many scientists uncomfortable.
It seems to give up on finding a deep reason for why the universe is the way it is, replacing explanation with mere selection. It seems too much like saying we won the cosmic lottery and there is nothing more to understand. Yet it may be correct. Just because an explanation is unsatisfying does not mean it is wrong. Other physicists suggest that perhaps the quantum foam itself has structure and rules that constrain what kinds of universes can emerge. Perhaps not all possible universes are equally probable. Perhaps there is some principle, some deep mathematical necessity that makes universes like ours far more likely to tunnel into existence than other kinds. This brings us to one of the most exciting frontiers in theoretical physics, the search for the initial conditions of the universe encoded in the structure of the quantum foam. Different approaches to quantum gravity make different predictions about what the quantum foam looks like and how it behaves. String theory suggests the foam might be a complex landscape with different valleys corresponding to different possible universes. Loop quantum gravity suggests spacetime might be built from discrete loops of gravitational field, giving the foam a kind of atomic structure. Causal set theory suggests spacetime emerges from a random sprinkling of points connected by causal relationships. Each of these approaches offers a different picture of the quantum substrate from which our universe emerged. And in principle, each makes different testable predictions. Perhaps patterns in the cosmic microwave background radiation carry signatures of the quantum foam. Perhaps gravitational waves from the earliest moments of the universe encode information about Planck scale physics. Perhaps observations of the universe at its largest scales can reveal the quantum structure at its smallest scales through subtle correlations and statistical patterns. We are still far from having definitive answers, but we are asking the right questions. We are probing reality at its deepest levels, investigating the quantum foam from which everything emerges. And we are finding that the boundary between something and nothing, between existence and non-existence, is far more subtle and strange than anyone imagined. The quantum foam does not respect our intuitive categories. It is neither being nor non-being, but something in between, a state of pure potential where all possibilities exist in superposition. Virtual particles are neither real nor unreal, but something that depends on how you measure them. Spacetime is neither continuous nor discrete, but exhibits properties of both depending on the scale at which you observe it. And, perhaps most unsettling of all, the quantum foam suggests that the distinction between past and future, between cause and effect, might also break down at the most fundamental level. In the quantum realm, effects can precede causes. Particles can travel backwards in time. Information can be transmitted from future to past. The neat causal chains that govern our macroscopic world dissolve into a web of quantum correlations that transcend temporal order. If the Big Bang emerged from the quantum foam, then perhaps asking what caused it is the wrong question. Perhaps causation itself is an emergent concept that only applies after the universe has expanded large enough and cooled enough for classical physics to be a good approximation. Perhaps in the quantum foam, there is no clear distinction between cause and effect. Only a complex web of quantum possibilities
that crystallize into a definite history only when observed from within the spacetime that emerges. This may sound like philosophical sophistry, but it has real implications for how we think about cosmic origins. It suggests that the universe might not need a cause in the traditional sense. It might simply be one particular configuration that emerges from the quantum foam, not because anything caused it to emerge, but because quantum mechanics allows it to emerge, and observation selects it from among all possibilities. The quantum foam is where physics meets metaphysics, where science approaches the ultimate questions of existence. It is the realm where something can come from nothing, because the distinction between something and nothing becomes meaningless. It is the place where time can begin, because time itself is an emergent property that does not exist in the underlying quantum state. And it is, quite possibly, where our universe began. The Cosmic Rewind. Let us take a journey backwards through time, not metaphorically, but as literally as physics allows. We will rewind the history of the cosmos, watching in reverse as galaxies rush together, stars grow younger, the universe becomes smaller, denser, hotter. We will travel back past the formation of Earth, past the birth of the Sun, past the deaths of ancient stars, all the way to the very edge of existence itself. And at each step, we will witness the universe becoming stranger, more extreme, until finally we reach a point where our understanding shatters completely. Begin now, in the present moment. You are reading these words in a universe that is nearly 14 billion years old. The cosmos around you is vast, almost beyond comprehension. If you could somehow travel at the speed of light, it would take you 100,000 years just to cross our galaxy. And our galaxy is merely one among hundreds of billions scattered through observable space. The distances are so enormous that light from the farthest galaxies has been traveling toward us since shortly after the Big Bang, crossing billions of light-years of space to reach our telescopes. But the universe was not always this large. It has been expanding, growing larger with each passing moment. Every galaxy is moving away from every other galaxy, carried along by the expansion of space itself. This is not because galaxies are moving through space, but because space itself is stretching, like dots drawn on the surface of an inflating balloon. And if the universe is expanding now, that means it was smaller in the past. Rewind time by a few billion years. The universe is noticeably smaller, perhaps 2/3 its current size. Galaxies are closer together. The light from distant objects is less redshifted, because it has not traveled through as much expanding space. But otherwise, things look fairly similar. Stars shine. Planets orbit. The laws of physics operate exactly as they do today. Go back further, about 5 billion years. The Sun does not exist yet. The cloud of gas and dust that will eventually collapse to form our solar system is still dispersed through space. Earth, all the planets, everything we know and love does not yet exist. But the universe is full of other stars, other planets, other worlds. The cosmic story is already billions of years old. Push back 10 billion years, more than 2/3 of the way to the Big Bang. The universe is less than half its current size. Galaxies are smaller and more irregular. Many of the heavy elements that make up planets and living things
have not yet been forged in stellar cores. The universe is younger, rougher, more violent. Massive stars burn bright and die quickly, exploding as supernovae and seeding space with the raw materials for future generations of stars. 13 billion years ago, we are now in the early days of galaxy formation. The first stars ignited only a few 100 million years before this moment. Before that, the universe was dark, filled only with hydrogen and helium gas, slowly collapsing under its own gravity. This period is called the Cosmic Dark Ages, and it lasted hundreds of millions of years. The universe existed, but nothing shone within it. No stars, no galaxies. Just vast clouds of gas gradually growing denser. Rewind through the Dark Ages. Watch as the young stars wink out of existence in reverse, their nuclear fires extinguished as if someone turned off a light switch. The gas clouds that formed them disperse backward into a more uniform distribution. The universe becomes simpler, smoother, more homogeneous. Now we arrive at a critical moment, roughly 380,000 years after the Big Bang. This is the epoch of recombination, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, the universe was too hot for atoms to exist. It was a plasma, a soup of charged particles, where photons could not travel far before being absorbed or scattered. The universe was opaque, like being inside a thick fog. But at recombination, something magical happened. The electrons combined with protons, leaving the photons free to travel unimpeded through space. The fog cleared. Light could suddenly stream across the universe. And that light, stretched and cooled by nearly 14 billion years of cosmic expansion, is what we observe today as the cosmic microwave background radiation. It is a baby picture of the universe, an image of the cosmos as it appeared when it was less than 400,000 years old. Before recombination, we cannot see directly. No light from that era survives in a form we can detect, but we can calculate what must have happened using our understanding of physics, and the calculations paint a picture of a universe growing ever more extreme. Rewind to 1 second after the Big Bang. The entire observable universe, everything that will eventually become hundreds of billions of galaxies, is compressed into a region smaller than our solar system. The temperature is 10 billion degrees, hot enough that even atomic nuclei cannot exist. The universe is a seething plasma of protons, neutrons, electrons, photons, and exotic particles that no longer exist in nature today. But even at this extreme temperature and density, the physics is still comprehensible. We have tested our theories at similar energies in particle accelerators. We understand how particles behave, how they interact, how matter and antimatter annihilate each other. This is the era of Big Bang nucleosynthesis, when the first atomic nuclei formed. Protons and neutrons fused together to create deuterium, helium, and trace amounts of lithium. The relative abundances of these light elements, measured in ancient stars and primordial gas clouds, match the predictions of Big Bang nucleosynthesis with remarkable precision. This is some of the strongest evidence we have that the hot Big Bang actually happened. Before 1 second, things become increasingly uncertain.
The temperatures rise above 10 billion degrees, then 100 billion, then a trillion. At 1/10,000th of a second after the Big Bang, the temperature reaches 10 trillion degrees. This is the energy regime explored by the Large Hadron Collider, the most powerful particle accelerator ever built. At these temperatures, even protons and neutrons cannot exist as distinct particles. They melt into a quark-gluon plasma, a soup of fundamental constituents that normally never exist in isolation. We have actually created this state of matter in our laboratories by smashing heavy nuclei together at nearly the speed of light. For a brief instant, a tiny speck of the universe is returned to the state it existed in during the first microseconds after the Big Bang. And by studying this quark-gluon plasma, we learn about the conditions in the early universe. But we can only probe so far. The highest energies we can achieve in accelerators correspond to the universe at about 1/trillionth of a second after the Big Bang.
Before that, we are extrapolating, using theories that have not been tested experimentally at such extreme conditions. Rewind to 1/trillionth of a second. The temperature is now a quadrillion degrees. At this energy, the electromagnetic force and the weak nuclear force, two of the four fundamental forces of nature, merge into a single unified electro-weak force. This is a real transition, predicted by theory and confirmed by experiments that earned the Nobel Prize. In the modern cold universe, these forces appear distinct, but in the heat of the early universe, they were unified. This suggests something profound. Perhaps all the forces of nature were once united, splitting apart as the universe cooled like water freezing into ice or steam condensing into water. Perhaps there is a fundamental simplicity underlying the apparent complexity of nature, a unity that existed at the beginning and was broken as the universe evolved. Go back further still, to 1/10 trillionth of a second after the Big Bang. We are now at energies that have never been tested in any laboratory. The temperature exceeds 10 trillion degrees. At this scale, according to some theories, the strong nuclear force also unifies with the electro-weak force, leaving only gravity separate. This is the era of grand unification, and it might explain some puzzling features of our universe. For instance, there is a mystery about the asymmetry between matter and antimatter. For every particle of matter created in the Big Bang, an equal amount of antimatter should have been created. When matter and antimatter meet, they annihilate each other in a burst of pure energy. So why is our universe made of matter? Where did all the antimatter go? Grand unified theories suggest that in the earliest moments there were subtle processes that created a tiny excess of matter over antimatter, perhaps one extra matter particle for every 10 billion matter-antimatter pairs. The pairs annihilated, leaving behind that tiny excess, which became everything we see today. But even grand unification is not the end of the story. Rewind to the Planck time, about 10 to the power of -43 seconds after the Big Bang. At this moment, the temperature reaches the Planck temperature, about 10 to the power of 32 degrees. This is not just hot. This is the highest temperature that has any meaning in physics. Above this temperature, quantum fluctuations in spacetime become so large that the very concepts of space and time break down. At the Planck time, we reach the edge of known physics. General relativity breaks down because quantum effects on space-time itself become enormous. Quantum mechanics breaks down because gravity becomes strong enough to create black holes from quantum fluctuations. Neither theory alone is adequate.
We need a theory of quantum gravity, and we do not have one that everyone agrees on. This is the wall we hit, the place where our equations fill with infinities and nonsense, the point where we can no longer reliably calculate what happens. Everything before the Planck time is speculation, educated guessing based on incomplete theories. We are extrapolating far beyond the regime where our physics has been tested. Yet we must try to peer beyond this wall, because this is where the deepest mysteries lie. What happened at the Planck time? Was there anything before it? Did time itself begin here? Or was this merely a transition from some prior state? These are not idle philosophical questions. They are scientific questions with potentially observable consequences. Some theories suggest that the universe underwent a period of exponential expansion called inflation just after the Planck era. In a tiny fraction of a second, the universe grew by a factor of at least 10 to the power of 26, doubling in size every 10 to the power of negative 37 seconds or so.
This incredible expansion would have stretched quantum fluctuations in the early universe to cosmic scales, providing the seeds for all the structure we see today, the slight variations in density that eventually grew into galaxies and clusters. We have evidence for inflation. The patterns in the cosmic microwave background radiation match the predictions of inflationary theory with stunning precision. The universe is geometrically flat, as inflation predicts. The distribution of galaxies on large scales matches what we expect from quantum fluctuations stretched to cosmic size. But what caused inflation? And what happened before it? This is where different theories diverge wildly. Some suggest inflation emerged from quantum tunneling in the landscape of possible vacuum states. Others suggest it was triggered by the collision of higher dimensional membranes. Still others suggest inflation is eternal, constantly creating new universes in an infinite cosmic foam, with our Big Bang just one bubble in an endless froth. As we try to rewind past the Planck time, we find not a single cosmic history, but a branching tree of possibilities. Without a complete theory of quantum gravity, we cannot determine which path is correct. We can only explore the possibilities and look for ways to test them against observation. But one thing seems clear. The closer we get to the Big Bang, the more extreme, bizarre, and incomprehensible the universe becomes. The familiar laws of physics give way to something stranger. Space and time lose their clear meaning. Cause and effect become tangled. The universe transforms from something comprehensible to something that defies imagination. And yet, through all of this, one fact remains. The universe exists. It expanded from an incredibly hot, dense state. It cooled and evolved, and eventually produced stars, planets, and life. We can trace its history backward with remarkable precision for the first billionth of a second. We can make educated guesses about what happened even earlier, down to times so short they make an eye blink seem like an eternity. The cosmic rewind has brought us to the edge of knowledge, to the boundary where physics meets mystery. We stand at the precipice of the Planck era, looking back toward the infinite density and temperature of the initial singularity, and forward into the universe we inhabit. Behind us lies the question of what came before. Before us
lies the reality that somehow, impossibly, emerged from those inconceivable conditions. The journey backward has shown us how far we have come in understanding our cosmic origins, but it has also shown us how far we still have to go. The singularity problem. There is a word that physicists use with a mixture of dread and fascination. A word that represents the ultimate breakdown of everything we understand about the universe. A word that signals the point where mathematics itself gives up and throws its hands in the air. That word is singularity. In everyday language, singular means unique or exceptional. In mathematics, it means something far more troubling. A singularity is a point where equations break down, where quantities become infinite, where the normal rules cease to apply. Divide any number by 0 and you get a singularity. Your calculator displays an error. The operation is undefined. Mathematics has nothing to say about what happens at that point. And according to general relativity, at the moment of the Big Bang, the universe was a singularity. All of space compressed to 0 volume. All the mass and energy of the universe squeezed into a single point with infinite density. Curvature of spacetime becoming infinite. Temperature rising to infinity. Every physical quantity that we can measure or calculate diverging toward impossible values. This is not a small problem that physicists can wave away or ignore. This is a fundamental crisis at the heart of cosmology.
Our best theory of gravity and spacetime. A theory that has passed every experimental test we can devise. A theory that predicted black holes and gravitational waves and the expanding universe itself. Tells us that if we run time backward far enough, we arrive at a point where that same theory breaks down completely and can tell us nothing. Einstein himself was deeply troubled by singularities. When his equations predicted that stars could collapse to infinite density, forming what we now call black holes, he tried to find arguments for why this could not actually happen in nature. He hoped there might be some physical mechanism that would prevent collapse before the singularity formed. He was wrong. Black holes exist, and at their centers, general relativity predicts singularities where density and curvature become infinite. But at least with black holes, the singularity is hidden behind an event horizon, a boundary beyond which nothing, not even light, can escape. The singularity cannot be seen from the outside. Whatever incomprehensible physics happens there cannot affect the rest of the universe. Roger Penrose and Stephen Hawking proved this rigorously in the 1960s with their singularity theorems. They showed that under very general conditions, singularities are inevitable in general relativity. But they also showed that cosmic censorship should hold, that singularities should always be hidden inside black holes where they cannot harm us. The Big Bang singularity is different. It is not hidden behind an event horizon. It is naked, exposed, in the past light cone of every event in the universe. Everything that exists emerged from this singularity. There is no way to isolate it, no way to ignore it, no way to avoid the fact that our entire universe apparently came from a point where physics breaks down. This should not be possible. A theory that predicts its own breakdown is telling us that something is wrong.
Either the singularity is not real,
or our theory is incomplete. Most physicists believe it is the latter. General relativity is not the final word on gravity and space-time. It is an approximation, extraordinarily accurate under most conditions, but an approximation nonetheless. And at the extreme conditions near the Big Bang singularity, that approximation breaks down. The problem is that general relativity is a classical theory. It treats spacetime as a smooth, continuous fabric and ignores quantum effects. This is perfectly fine for large scales, like planets orbiting stars or galaxies moving through space. Quantum effects are utterly negligible at those scales. But at the Planck scale, quantum effects become dominant, and a classical theory simply cannot capture what is happening. Imagine trying to describe water using only the laws that govern solid objects. You could get pretty far. You could describe waves as oscillations, currents as flows, even predict many behaviors reasonably well. But eventually, you would encounter phenomena, turbulence, phase transitions, surface tension, that cannot be understood without recognizing that water is made of discrete molecules. The continuum approximation breaks down. You need a molecular theory. Similarly, general relativity treats spacetime as a continuum, but at the Planck scale, this approximation must break down. Spacetime must have some kind of discrete or quantum structure that becomes important at extreme energies and densities, and that quantum structure should resolve the singularity, replacing the infinite density and curvature with something finite, something comprehensible, something that quantum mechanics can describe. But here is where we run into a profound difficulty. We do not have a complete, tested theory of quantum gravity. We have several candidate theories, each with its own approach to quantizing spacetime, but none has been definitively confirmed by experiment. And without such a theory, we cannot reliably calculate what replaces the singularity. We are like astronomers before the telescope, making educated guesses but unable to actually see what is there. Different approaches to quantum gravity suggest different resolutions to the singularity problem. In string theory, particles are not point-like objects but tiny vibrating strings. The string has a characteristic length scale, roughly the Planck length, and this provides a natural cutoff. Distances shorter than the string length have no physical meaning. When you try to probe to smaller scales, you actually start probing larger scales again due to a symmetry called T-duality. In this framework, the Big Bang singularity might be replaced by a minimum length scale. The universe could never be compressed smaller than the string length, so density and temperature would remain finite. Loop quantum gravity takes a different approach. It quantizes spacetime itself, treating it as a network of discrete loops rather than a smooth continuum. Space becomes granular at the Planck scale, built from indivisible atoms of volume. In this picture, the Big Bang singularity is replaced by a big bounce. As the universe contracts toward the would-be singularity, quantum effects create a repulsive force that halts the collapse and reverses it. The universe bounces, transitioning from contraction to expansion without ever reaching infinite density. Causal set theory suggests yet another possibility. Spacetime emerges from a discrete set of points connected by causal relationships. The apparent continuity of spacetime is like the apparent continuity of a digital photograph. an illusion created by averaging over many discrete elements. In this framework, asking what happens at the singularity is like asking what happens between pixels. The question assumes a resolution that does not exist at the fundamental level. Each of these approaches has its merits and its challenges. String theory is mathematically elegant and unifies all forces including gravity, but requires extra dimensions of space and has yet to make contact with experimental reality. Loop quantum gravity is more conservative, working directly with general relativity and quantum mechanics without adding new ingredients, but struggles to recover the smooth spacetime of general relativity at large scales. Causal set theory offers a radical reconceptualization of spacetime, but faces difficulties in deriving the detailed structure we observe. What they all have in common is the promise of resolving singularities. They all suggest that infinite densities and curvatures are artifacts of treating spacetime as a classical continuum. Once quantum effects are properly included, the infinities disappear, replaced by extreme but finite conditions that quantum gravity can describe. This would be a profound resolution to the singularity problem. It would mean the Big Bang was not truly the beginning, not a moment of creation from nothing, but rather a transition. The universe might have existed in some form before the Big Bang, perhaps as a contracting phase that bounced, or as a different kind of geometry that transitioned to our expanding spacetime, or as part of a larger multiverse structure that gave birth to our local universe. But even if quantum gravity resolves the classical singularity, we are still left with deep questions. Why did the universe have the particular quantum state it had at the moment of the bounce or transition? What determined the initial conditions? Why was entropy so low, creating the arrow of time we experience? These questions push us back further, toward an even earlier state or condition that set the stage for what we call the Big Bang. Some physicists argue that we are asking the wrong questions. Perhaps there is no ultimate explanation, no final cause, no deepest level where everything is resolved. Perhaps the universe simply is, and asking why is like asking why mathematics is true, or why logic works. These are not questions with answers, but rather the foundations on which all questions and answers rest. Others insist that we must keep pushing, that there must be a reason, an explanation, a deeper truth. The history of science is filled with mysteries that seemed inexplicable until someone found the right insight. The motion of planets seemed inexplicable until Newton discovered gravity. The origin of species seemed inexplicable until Darwin discovered evolution. The behavior of atoms seemed inexplicable until quantum mechanics was developed. Why should the origin of the universe be different? There is also a more disturbing possibility. Perhaps the singularity is telling us something fundamental about the limits of knowledge itself. Perhaps there are questions that cannot be answered, not because we lack the intelligence or technology, but because the universe itself places boundaries on what can be known. The singularity might be such a boundary, a horizon beyond which information cannot pass, where the causal structure of spacetime breaks down so completely that no amount of observation or calculation can reveal what lies beyond. This would not be unprecedented. Quantum mechanics already teaches us that certain quantities cannot be known simultaneously with arbitrary precision. The uncertainty principle is not a limitation of measurement, but a fundamental feature of reality. Perhaps there are similar fundamental limitations on what we can know about cosmic origins. Perhaps the information about what preceded the Big Bang, if anything did precede it, is simply not encoded in the observable universe. The past beyond a certain point might be literally unknowable, not hidden, but non-existent in any meaningful physical sense.
Roger Penrose has argued that singularities might actually be essential features of the universe, not bugs to be eliminated, but rather profound statements about the nature of existence. He suggests that at a singularity, the normal rules of physics are suspended, allowing for a kind of freedom that does not exist elsewhere. Perhaps the Big Bang singularity represented a moment of pure possibility, where the laws of physics themselves came into being, chosen from a vast landscape of mathematical possibilities. This is a deeply philosophical position, verging on the metaphysical, but it highlights an important point. When we confront the singularity, we are not just dealing with a technical problem in physics. We are confronting the ultimate questions of existence, meaning, and causation. We are asking why there is something rather than nothing, and whether that question even makes sense. The singularity problem also connects to questions about the nature of time. If time itself began at the Big Bang, as many interpretations of general relativity suggest, then asking what came before is meaningless. There is no before. The singularity is not a moment in time, but rather the boundary or beginning of time itself. Asking what caused the Big Bang is like asking what caused time, which may be a category error. But if quantum gravity resolves the singularity, replacing it with a bounce or transition, then time might extend before the Big Bang. There might be a genuine history that precedes our universe. And if so, we need to understand what that history was and how it gave rise to the conditions we observe. The search for an answer has led to some of the most creative and bizarre proposals in the history of science. Universes giving birth to other universes through black holes. Eternal inflation creating infinite pocket universes. Cyclic cosmologies where the universe repeats endlessly. Colliding brains in higher dimensions. Each proposal attempts to explain how our universe could emerge from some prior state without requiring an initial singularity. Yet every proposal faces the same fundamental challenge. If you explain the Big Bang by appealing to some prior state or structure, you must then explain that prior state or structure. The explanatory regress seems infinite. You can always ask what came before, what caused that, what determined those initial conditions. Unless, that is, you can find a state or principle that is truly fundamental, that requires no further explanation because it is logically necessary, or because it generates itself from pure mathematics or quantum indeterminacy. This is the holy grail of cosmology, a theory that explains why the universe exists, why it has the properties it does, and why those properties were inevitable given the fundamental laws of logic and mathematics. Such a theory would eliminate the singularity not by replacing it with some prior physical state, but by showing that the universe is a necessary consequence of the structure of possibility itself. We are very far from such a theory, but the fact that serious scientists are pursuing it, developing mathematical frameworks and making testable predictions, shows how far cosmology has come. We are no longer content to simply describe the universe as we find it.
We want to understand why it must be this way, or whether it could have been different, and what that tells us about the deepest nature of reality. The singularity stands before us like a wall, blocking our view of what lies beyond. But walls can be climbed, tunneled through, or perhaps revealed to be illusions. The singularity may be the ultimate mystery, or it may be the key that unlocks an even deeper understanding. Either way, it remains the central challenge in our quest to understand the universe that should not exist. Eternal inflation and the multiverse. Imagine a pot of water on a stove just beginning to boil.
At first, a single bubble forms at the bottom where the heat is most intense.
Then another bubble appears, and another. Soon the pot is filled with countless bubbles, each expanding rapidly, some merging together, others breaking the surface and disappearing. Now imagine that this process never stops. The pot is infinite. The water never runs out. Bubbles form eternally, creating an endless froth that extends forever in all directions and persists for all time. This is eternal inflation, one of the most profound and controversial ideas in modern cosmology. And if it is correct, our entire universe, with its 100 billion galaxies and its 13.8 billion-year history, is just one bubble in an infinite cosmic foam. The Big Bang was not the beginning of everything. It was merely the beginning of our bubble, our local patch of the greater cosmos. And beyond our bubble, separated by regions of space still inflating at exponential rates, lie other bubbles, other universes, other Big Bangs, perhaps with different laws of physics, different fundamental constants, different dimensionalities of space and time. This is not science fiction. This is a serious scientific hypothesis that emerges naturally from our best theories of the early universe. And if true, it transforms our understanding of cosmic origins in the most radical way imaginable. The story of eternal inflation begins with regular inflation, the theory developed in the 1980s to solve several puzzling problems about the Big Bang. One of these problems is the horizon problem. When we look at the cosmic microwave background radiation coming from opposite sides of the sky, we find that these regions have almost exactly the same temperature. But according to standard Big Bang cosmology, these regions should never have been in causal contact. Light has not had enough time since the Big Bang to travel between them.
So how did they reach the same temperature? How did they know to be in thermal equilibrium? Inflation solves this by proposing that the universe underwent a brief period of exponential expansion in its earliest moments. During this expansion, space itself grew faster than the speed of light, doubling in size every tiny fraction of a second. A region small enough to be in thermal equilibrium was stretched to encompass the entire observable universe and far beyond. The uniformity we observe is inherited from this tiny initial patch that was in equilibrium before inflation began. This idea works beautifully. It explains not just the horizon problem, but also why the universe is so geometrically flat, why we do not observe magnetic monopoles and other exotic relics predicted by grand unified theories, and where the tiny density fluctuations that seeded galaxy formation came from. Quantum fluctuations during inflation would have been stretched to cosmic scales, creating exactly the pattern of variations we observe in the cosmic microwave background. But inflation comes with an unexpected consequence. Once inflation starts, it is very difficult to stop everywhere simultaneously. Imagine that inflation is driven by a quantum field, called the inflaton field, sitting in a high-energy state. For inflation to end, this field must decay to a lower energy state, like a ball rolling down a hill. When the field reaches the bottom of the hill, inflation stops, and the energy is converted into matter and radiation, creating what we call the Big Bang. The problem is that this process is governed by quantum mechanics, and quantum mechanics is probabilistic. Some regions of space will transition out of the inflating state quickly, others will take longer, and while a region is still inflating, space is doubling in size every fraction of a second. So even if most of the volume transitions out of inflation, the regions still inflating grow so rapidly that they more than compensate for the loss. The total volume of inflating space actually increases with time, even as local regions stop inflating and become normal universe. This is eternal inflation. Once inflation starts anywhere in the cosmos, it never truly ends. It continues forever, with local regions constantly transitioning out and becoming pocket universes like ours, while the inflating regions between them grow exponentially. The result is an infinite fractal structure, a tree that branches endlessly, with each branch representing a universe like ours. Alan Guth, one of the founders of inflation theory, describes it this way: inflation is like a magic trick where the magician pulls a rabbit out of a hat, then pulls another rabbit out of the first rabbit, then pulls another rabbit out of that rabbit, forever. Each rabbit contains the potential to produce more rabbits. The trick never ends because the raw material, inflating space, reproduces faster than it is consumed. This has staggering implications. If eternal inflation is correct, then our universe is not unique. There are infinitely many other universes, each with its own Big Bang, its own history, its own structure. Most of these universes are forever beyond our ability to observe or communicate with. They are separated from us by regions of space still inflating exponentially, regions that are growing faster than light can cross them. We are causally disconnected, isolated in separate bubbles that will never touch. But it gets stranger still. According to modern particle physics, the laws of nature we observe might not be unique. String theory, which attempts to unify all forces including gravity, suggests there is a vast landscape of possible vacuum states, each corresponding to different effective laws of physics. Different arrangements of extra dimensions, different values of fundamental constants, different particles and forces. The number of possibilities is immense, perhaps 10 to the power of 500 or more. In eternal inflation, different pocket universes could settle into different vacuum states. One universe might have a strong gravitational force and a weak electromagnetic force. Another might have 6 dimensions of space instead of 3. Yet another might have completely different particles and forces that we could not even recognize. Each bubble in the eternal inflation froth could be a different universe with different physics. This is the multiverse hypothesis. Not just many universes, but many kinds of universes, exploring the full range of physical possibilities. And somewhere in this infinite ensemble, purely by chance, there must be universes like ours where the physical constants are just right for stars to form, planets to coalesce, chemistry to become complex, and life to emerge. This provides a potential answer to one of the deepest mysteries in physics, the fine-tuning problem. The laws of physics in our universe appear remarkably special, almost custom-designed to allow for complexity and life. If the strength of gravity were slightly different, stars could not form. If the strong nuclear force were slightly weaker, no atomic nuclei beyond hydrogen could exist. If the cosmological constant were much larger, space would expand so rapidly that galaxies could never form. There are dozens of such apparent coincidences, and they have puzzled physicists for decades. In a single universe,
This fine-tuning seems almost miraculous. It demands an explanation. Why are the constants so perfectly balanced? But in an infinite multiverse, fine-tuning is not surprising at all. Most universes will be sterile and lifeless, with random values of the constants that do not permit complexity. But some tiny fraction will have the right conditions.
And we inevitably find ourselves in one of those rare universes because we could not exist anywhere else. This is the anthropic principle applied to the multiverse. Our existence selects, from the vast ensemble of possibilities, only those universes capable of producing observers. Many physicists find this deeply unsatisfying. It seems to replace prediction with post-diction, explanation with selection. Science is supposed to explain why things are the way they are, not just say they could be many ways and we happen to observe one of them. It feels like giving up on finding a deeper reason for the laws of physics. But others argue that this may simply be how nature works. Not everything requires a deeper explanation. The fact that Earth is at the right distance from the Sun for liquid water does not require a fundamental theory. It is selection. Among the billions of planets in our galaxy, some will be in the habitable zone, and life will naturally arise on those planets to wonder why conditions are so perfect. Perhaps the constants of physics are similar. Among infinite universes with different constants, some will permit life, and that is where observers will find themselves. The challenge is that the multiverse hypothesis seems untestable. If other universes are forever beyond our ability to observe, how can we ever confirm they exist? How can we test a theory that makes predictions about things we cannot see? Does this even qualify as science? Or has it crossed into metaphysics and philosophy? Surprisingly, there may be ways to test eternal inflation and the multiverse, at least indirectly. If our universe nucleated from eternal inflation, this process should have left signatures that we can potentially observe. For instance, if two bubble universes collided in the distant past before moving apart, the collision would create a distinctive pattern in the cosmic microwave background radiation. We have looked for such patterns and found nothing so far, but the search continues with increasingly sensitive instruments. Another potential test comes from the distribution of physical constants. If the multiverse is real, and different universes have different constants, then we should expect to find ourselves in a typical universe among those capable of producing observers. We can calculate what typical means and check whether our universe fits that description. Some analyses suggest our cosmological constant, the energy density of empty space, is roughly what we would expect if it were randomly selected from a distribution of values that allows for galaxy formation. This is weak evidence, but it is evidence nonetheless. There are also more speculative ideas. Some physicists have proposed that black holes might give birth to new universes, creating a kind of cosmic natural selection, where universes that produce many black holes also produce many offspring universes. If this is true, most universes in the multiverse would be descendants of universes optimized for black hole production, and we could make predictions about what typical physical constants should be. Lee Smolin developed this idea into a full theory he calls cosmological natural selection. Just as biological evolution operates through variation and selection, cosmic evolution might operate through universe reproduction and selection. Universes with physical constants that allow for black hole formation produce more offspring universes, and over cosmic time,
these universes dominate the population. Our universe should have physical constants close to those optimal for black hole production, and Smolin argues that this is indeed what we observe. But eternal inflation and the multiverse raise profound philosophical questions beyond just testability.
If there are infinitely many universes, and in an infinite ensemble every possible history occurs infinitely many times, then what does it mean for something to be unlikely? If every possible event happens somewhere, how do we make predictions? How do we even assign probabilities? This is the measure problem in cosmology. One of the most challenging conceptual issues in eternal inflation. When you have an infinite multiverse, you cannot simply count universes to calculate probabilities. Infinity divided by infinity is undefined. You need to specify a procedure for measuring volumes or probabilities, and different procedures give different answers. There is no unique, objective way to compute what is typical or likely in an infinite multiverse. Some physicists see this as a fatal flaw in eternal inflation. If the theory cannot make definite predictions, if it depends on arbitrary choices about how to measure probabilities, then perhaps it is not really a scientific theory at all. Others see it as a challenge to be overcome, requiring new conceptual frameworks for thinking about probabilities in infinite ensembles. There is also a disturbing consequence known as the Boltzmann brane problem. In an eternally inflating universe, quantum fluctuations can occasionally produce organized structures by pure chance. Most fluctuations produce nothing interesting, just random arrangements of particles. But very rarely a fluctuation might produce something complex, like a brain, with false memories of an entire life history. In an infinite multiverse with infinite time, such Boltzmann branes would actually be far more common than branes that evolve naturally through the history of a universe like ours. This leads to a bizarre conclusion. If you accept eternal inflation, you should conclude that you are probably a Boltzmann brane, a random fluctuation with false memories, rather than a real person in a real universe. But this is obviously absurd. You know you are real. Your memories are genuine. Your experiences are not random fluctuations. So either eternal inflation is wrong, or we are making a mistake in how we calculate probabilities in an infinite multiverse. Various solutions have been proposed, but none are entirely satisfying. Some argue that we should weight probabilities by complexity, making Boltzmann branes less likely despite their greater numbers. Others suggest that eternal inflation must eventually end through some mechanism we do not yet understand, preventing the accumulation of infinite numbers of Boltzmann branes. Still others bite the bullet and accept that we cannot trust our observations or memories if eternal inflation is true, which seems to undermine the entire scientific enterprise. Despite these challenges, eternal inflation remains popular among cosmologists because it emerges naturally from inflation, which is strongly supported by observations. It is not an ad hoc addition, but rather an unavoidable consequence of the dynamics of inflationary fields. If inflation happened, eternal inflation probably happened. And if eternal inflation happened, the multiverse is real. This represents a remarkable transformation in how we think about cosmic origins. The Big Bang is no longer the ultimate beginning, but rather a local event, the birth of our bubble in an eternally inflating cosmos. The question of what came before the Big Bang has an answer.
eternal inflation, a process that has no beginning and no end, constantly producing new universes like ours. But this answer raises new questions. Where did eternal inflation itself come from? Did it have a beginning? Or is it truly eternal, extending infinitely into the past? Is there some even deeper level of reality from which eternal inflation emerged? Or is the inflating state the ground of all being, the ultimate reality that requires no further explanation? These questions push us toward even more speculative territory, toward theories of quantum cosmology that attempt to describe the wave function of the entire universe, or toward the idea that the multiverse is the realization of all mathematical possibilities, or toward cycles of creation and destruction that repeat eternally. We are at the frontiers of knowledge, where physics blends with philosophy, and speculation becomes increasingly difficult to distinguish from science. Yet we continue to push forward, because the alternatives are worse. We can accept ignorance and declare that some questions are forever beyond science. Or we can keep asking, keep theorizing, keep searching for ways to test even the most outrageous ideas. History suggests that the latter approach, however difficult and uncertain, is the one that leads to progress. The multiverse may be real. Our universe may be just one bubble in an infinite cosmic foam. And if so, the Big Bang was not the beginning of everything, just the beginning of our small corner of an infinitely larger reality. The cyclic universe. There is something deeply satisfying about the idea of cycles. Day follows night, night follows day. Seasons turn in their endless wheel. Living things are born, grow, reproduce, and die, only for their offspring to repeat the pattern. Even stars follow this rhythm, burning for billions of years before dying and scattering their ashes into space, where new stars eventually form from the enriched material. Cycles are everywhere in nature, patterns of repetition that give structure and meaning to the flow of time.
So it is natural to wonder whether the universe itself might be cyclic. Perhaps the Big Bang was not the absolute beginning, but rather a transition, a point in an eternal cycle of expansion and contraction. Perhaps our universe will eventually stop expanding, reverse course, and collapse back down in a big crunch, only to rebound in a new Big Bang that starts the cycle over again. Perhaps this has happened infinitely many times already, and will continue infinitely far into the future. This is the cyclic universe hypothesis, one of the oldest and most enduring alternatives to the standard Big Bang cosmology. And in recent years, it has experienced a remarkable renaissance, driven by new ideas from string theory and observations of dark energy that have transformed our understanding of cosmic evolution. The idea of a cyclic universe has ancient roots. Hindu cosmology describes cycles of creation and destruction lasting billions of years, with the universe repeatedly expanding from a point and collapsing back again. Friedrich Nietzsche proposed eternal recurrence, the idea that the universe must eventually return to exactly the same state it started in and repeat its entire history infinitely. These were philosophical and religious ideas, not scientific theories, but they captured an intuition that many people find compelling. The first scientific cyclic model came from Albert Einstein's general relativity.
The equations of general relativity allow for solutions where the universe expands from a Big Bang, reaches a maximum size, and then contracts back to a big crunch. This is called a closed universe, and for decades after Einstein developed his theory, many physicists thought this might be the true fate of the cosmos. In a closed universe, there is enough matter and energy that gravity eventually overcomes the expansion. The universe reaches a turning point, like a ball thrown upward reaching the peak of its arc, and begins to fall back. Galaxies that are now rushing apart would start to approach each other. The cosmic microwave background radiation, now stretched to long wavelengths by cosmic expansion, would be compressed to shorter wavelengths, gradually heating up. As the universe contracts, events would unfold in reverse order compared to the expansion phase. Galaxy clusters would merge. Galaxies would collide more frequently. Stars would be packed closer and closer together. Eventually, individual stars would be pulled apart by tidal forces as the density of the universe increased. Then atoms would be ionized as temperatures rose past thousands of degrees. Then atomic nuclei would be broken apart as temperatures exceeded billions of degrees. The universe would pass through all the same stages it experienced during expansion, but in reverse. The cosmic microwave background would become cosmic infrared, then visible light, then ultraviolet, then X-rays, then gamma rays. The sky would glow increasingly brightly as radiation from all directions was compressed and blue-shifted. Finally, the universe would approach a state similar to the Big Bang, all matter and energy compressed into an increasingly small volume, temperatures and densities rising toward infinity. But instead of calling it the Big Bang, in this scenario we call it the Big Crunch. All of space collapses to a point. All matter and energy compressed to infinite density. The universe ending in a singularity, just as it began from one. For a long time, physicists debated whether the universe had enough matter to eventually recollapse, or whether it would expand forever. Observations gradually revealed that the universe is close to the critical density, balanced on a knife edge between eternal expansion and eventual collapse. But in the late 1990s, observations of distant supernovae revealed something shocking. The expansion of the universe is not slowing down as everyone expected. It is speeding up. This discovery of cosmic acceleration earned the Nobel Prize and transformed cosmology. It implies the existence of dark energy, a mysterious component that fills all of space and pushes everything apart. Dark energy is the dominant component of the universe today, making up about 68% of the total energy density. And if dark energy remains constant or increases in the future, the universe will never recollapse. It will expand forever, accelerating toward an increasingly cold and empty state. This seemed to kill the cyclic universe hypothesis. How could the universe cycle if expansion never reverses? The Big Crunch scenario appeared to be ruled out by observation. But then physicists realized something remarkable. Perhaps the universe does not need to collapse to a point to cycle. Perhaps there is another way to achieve a cyclic cosmos that is consistent with cosmic acceleration. This insight led to a new generation of cyclic models, very different from the simple Big Bang, Big Crunch scenario, but potentially even more interesting. One influential model, developed by Paul Steinhardt and Neil Turok, proposes that our universe cycles not through expansion and contraction, but through collisions of higher dimensional membranes, or branes for short. This idea comes from string theory, which requires extra dimensions of space beyond the three we experience. In certain versions of string theory, our entire universe could be a three-dimensional brane floating in a higher dimensional space. Steinhardt and Turok imagined two branes separated by a small distance in the extra dimension. These branes are attracted to each other by forces in the higher dimensional space. They slowly drift together, collide, bounce apart, and then gradually approach again. Each collision releases enormous energy along the branes, creating what we perceive from within our brain as a Big Bang. Matter and radiation are produced, the universe expands and cools, structure forms, stars and galaxies appear, and eventually the energy dissipates. Meanwhile, the other brane has drifted away and is now slowly approaching again. The approach takes trillions of years, but eventually another collision occurs. This new collision wipes the slate clean, destroying all existing structure and producing new matter and radiation. A new cycle begins, with no memory of what came before, except perhaps in subtle correlations imprinted in the quantum fluctuations that seed structure formation. In this model, the Big Bang is not the beginning of time, but rather a transition, a collision event that marks the start of a new cycle. Time extends infinitely into the past and future, with cycles repeating eternally. There is no singularity, no moment of infinite density, because the branes never collapse to zero size. They maintain their structure through the collision, bouncing apart before any singular conditions can develop. This resolves the singularity problem in an elegant way. Instead of trying to understand what happened at infinite density, we only need to understand the physics of brane collisions, which, while exotic and untested, at least involve finite energies and densities that quantum field theory on the branes can potentially describe. The cyclic model also offers potential explanations for puzzles like the flatness and horizon problems that standard inflation was invented to solve. The long periods between collisions allow the universe to stretch and flatten naturally. The collision itself can create correlations across the entire brane, explaining why distant regions of the universe appear to be in thermal equilibrium. But the cyclic model faces significant challenges. For one thing, it requires extra dimensions and branes, which we have no direct evidence for. String theory remains unproven, and the specific scenario of colliding branes is highly speculative. We do not fully understand the physics of brane collisions, so predictions are uncertain and difficult to test rigorously. There is also a thermodynamic problem. Each cycle should increase the total entropy of the universe, as required by the second law of thermodynamics. But after infinitely many cycles, the entropy should be infinite, and the universe should be in a state of maximum disorder. Yet we observe a universe with relatively low entropy, high structure, and organization. How can this be reconciled with an infinite past of cyclic evolution? Steinhardt and Turok argue that entropy is diluted during the long expansion phases between collisions. As the branes separate and space expands, the entropy per volume decreases, even though total entropy increases. By the time of the next collision, conditions are essentially reset, allowing the cycle to continue indefinitely without running down into heat death. Critics remain skeptical. Calculating entropy reliably in quantum field theories on dynamical backgrounds is notoriously difficult, and there is debate about whether the proposed mechanism actually works. Some argue that subtle quantum effects would cause information to accumulate across cycles, eventually degrading the bounces and causing the cyclic behavior to break down. There is also the question of how the cyclic behavior started. If cycles have continued eternally into the past, then the universe has no beginning, which resolves one mystery but replaces it with another. If cycles began at some point, we need to explain what came before and what triggered the first cycle. Either way, we have not fully escaped the problem of cosmic origins. Despite these challenges, cyclic models remain an active area of research because they address fundamental questions in new and creative ways. They suggest that the Big Bang, while dramatic and significant, might not be fundamentally special.
It is simply what happens when brains collide, or when quantum bounces reverse a contracting phase. The focus shifts from understanding the beginning of time to understanding the physics of transitions between phases of cosmic evolution. Another approach to cyclic cosmology comes from loop quantum gravity, which we mentioned earlier in the context of resolving singularities. In loop quantum cosmology, quantum effects become important when the universe is extremely dense, preventing collapse to infinite density and instead causing a bounce. The universe contracts to a minimum volume, then expands again. In this framework, our Big Bang was preceded by a big crunch from a previous cycle. That previous universe existed and evolved until it reached a point where it began to contract. The contraction continued until quantum gravity effects halted it and reversed it, creating the bounce we call the Big Bang. And in the far future, our universe might undergo the same fate, contracting until quantum effects produce another bounce, starting the next cycle. Loop quantum cosmology makes detailed predictions about the structure of the universe that might be testable. The quantum bounce should leave specific signatures in the cosmic microwave background radiation, patterns of correlations that differ from those produced by standard inflation. So far, observations have not detected these signatures, but the search continues, and future experiments might provide definitive tests. Roger Penrose has proposed yet another type of cyclic cosmology, which he calls conformal cyclic cosmology, or CCC. This model is based on a radical idea about the nature of time and the evolution of the universe toward its far future. Penrose observes that in the far future, assuming dark energy remains constant, the universe will expand exponentially forever. All matter will eventually decay into radiation. Stars will burn out, black holes will evaporate through Hawking radiation, and ultimately the universe will contain nothing but photons and other massless particles, spreading ever farther apart through ever-expanding space. But here is where Penrose makes a striking observation. In such a universe, with nothing but massless particles, there are no clocks. Massive particles, like atoms, can serve as clocks, oscillating at characteristic frequencies determined by their masses. But photons have no mass and no natural oscillation frequency.
time becomes ambiguous. And in general relativity, when there are no natural time standards, you can rescale time arbitrarily. The far future of one universe, with photons spread across infinite space, could be mathematically equivalent to the Big Bang of the next universe, where everything is compressed but also consists mainly of radiation. Penrose proposes that the universe undergoes a conformal transformation at the end of each eon, mathematically transforming the infinite future of one eon into the Big Bang of the next. There is no physical process connecting them, just a mathematical identification. The cycles are not separated by bounces or collisions, but rather by a kind of mathematical reset, where infinity becomes finite again. This is a deeply strange idea, and it relies on subtle properties of general relativity and the behavior of massless fields. Many physicists are skeptical, questioning whether the transformation Penrose proposes is physically meaningful or merely a mathematical curiosity. But Penrose argues that CCC makes testable predictions. He claims to have found signals in the cosmic microwave background that could be echoes from the previous eon, circular patterns that might represent the gravitational waves from colliding black holes in the universe that came before ours. These claims are controversial, and other researchers analyzing the same data have not found convincing evidence for the proposed signals. The debate continues, with Penrose defending his interpretation and critics arguing that the patterns can be explained by statistical fluctuations or instrumental artifacts. What all these cyclic models share is a deep dissatisfaction with the idea that the universe simply began from nothing at the Big Bang. They propose instead that the Big Bang is a transition, a bounce, a collision, or a conformal transformation connecting one phase of cosmic evolution to another. Time does not begin, but rather flows eternally, with the apparent beginning just a dramatic event in an infinite history. This perspective transforms the question of cosmic origins. Instead of asking what caused the Big Bang, we ask what physics governs the transitions between cycles. Instead of asking why the universe exists, we accept that it always has existed and focus on understanding its evolution. The mystery does not disappear, but it changes form, becoming a question about the nature of the cyclic process rather than about absolute beginnings. Whether any of these models is correct remains unknown. We do not yet have the observations or the complete theories needed to definitively test them. But they represent serious attempts by serious scientists to grapple with the deepest questions about existence and time. And they show that alternatives to the standard Big Bang cosmology are possible, that the universe we observe might be compatible with very different underlying structures and histories. The cyclic universe reminds us that time might be very different from what we intuitively imagine. Not a line with a beginning and an end, but perhaps a circle or a spiral, or an infinite sequence of events with no first moment. And if so, the question of what came before the Big Bang has a simple answer. Another cycle, another universe, another chapter in an eternal story that has no beginning and no end. Quantum loop gravity and the Big Bounce. There is a profound irony at the heart of modern physics. Our two greatest theories, quantum mechanics and general relativity, are each spectacularly successful in their own domains. Quantum mechanics describes the subatomic world with astonishing precision, predicting the behavior of particles, atoms, and light to extraordinary accuracy. General relativity describes gravity, space-time, and the cosmos with equal brilliance, explaining everything from the orbit of Mercury to the expansion of the universe itself. Yet, these two theories are fundamentally incompatible. They speak different mathematical languages, make contradictory assumptions about the nature of reality, and when we try to combine them, the mathematics explodes into nonsense. Nowhere is this incompatibility more problematic than at the Big Bang. As we rewind cosmic history toward the initial singularity, both quantum effects and gravitational effects become equally important. We need a theory that incorporates both. We need quantum gravity. And despite decades of effort, we still do not have a complete, experimentally verified theory that successfully merges quantum mechanics with general relativity. But we do have several promising approaches, and one of the most developed and conceptually radical is loop quantum gravity. Unlike string theory, which introduces new ingredients like extra dimensions and fundamental strings, loop quantum gravity attempts to quantize general relativity directly, applying quantum principles to space-time itself without adding anything new. The result is a theory where space and time are not continuous, but rather built from discrete quantum building blocks. And when applied to cosmology, loop quantum gravity makes a stunning prediction. There was no Big Bang singularity. Instead, there was a big bounce, a smooth transition from a contracting universe to our expanding universe, with no moment of infinite density, no breakdown of physics, no beginning of time.
To understand loop quantum gravity, we need to start with how general relativity describes space-time. Einstein taught us that space-time is not a fixed background, but rather a dynamic entity, a fabric that can be stretched, compressed, and warped by matter and energy. The equations of general relativity tell us how matter curves spacetime, and how curved spacetime tells matter how to move. This is gravity, not as a force acting across space, but as the geometry of spacetime itself. But what is spacetime made of? In classical general relativity, we treat it as a smooth continuum, infinitely divisible. You can always zoom in to finer and finer scales, and spacetime remains smooth. But quantum mechanics suggests that nothing in nature is truly continuous at the smallest scales. Energy comes in discrete quanta. Angular momentum is quantized. Even electric charge appears only in multiples of the electron charge. If quantum mechanics applies universally, then space-time itself should be quantized at small enough scales. Loop quantum gravity takes this idea seriously. It proposes that space-time has an atomic structure, built from indivisible units of volume and area, just as matter is made of atoms that cannot be subdivided while remaining matter. Space is made of fundamental quanta that cannot be subdivided while remaining space. The smooth geometry we experience is an emergent property, an average over countless discrete quantum elements, like how a digital photograph appears continuous when viewed from a distance, despite being composed of individual pixels. The mathematical implementation of this idea is technically complex, involving spin networks, holonomies, and quantum states of geometry. But the basic picture is elegant. Space is woven from quantum threads, loops of gravitational field that form a network.
These loops cannot be shrunk arbitrarily small.
There is a minimum length scale, the Planck length, roughly 10 to the power of -35 meters, below which the concept of distance loses meaning. Area and volume are similarly quantized, coming in discrete multiples of fundamental units. This quantum structure of space has profound consequences for understanding the Big Bang. In classical general relativity, as we rewind time toward the Big Bang, space contracts toward zero volume and density rises toward infinity. We hit a singularity where the theory breaks down. But in loop quantum gravity, space cannot contract to zero volume. There is a minimum possible volume determined by the quantum structure of space itself. The universe can compress only so far before quantum effects become dominant and halt the collapse. What happens at this critical density? The quantum geometry creates an effective repulsive force, a quantum bounce that reverses the contraction. The universe stops shrinking and begins expanding instead. This is not a new force of nature or a modification of the equations. It emerges naturally from applying quantum principles to the geometry of space. The bounce is inevitable, built into the quantum structure of space-time itself. This means the Big Bang was not a beginning, but a bounce. Before the bang, there was a crunch. A previous universe contracted under gravity, grew denser and hotter, but instead of collapsing to a singularity, it reached a critical quantum density and bounced, expanding outward to become our universe. The singularity is replaced by a quantum bridge, connecting a contracting phase to an expanding phase. Abhay Ashtekar, Martin Bojewald, and others have developed detailed mathematical models of this quantum bounce within the framework of loop quantum cosmology, the application of loop quantum gravity to the universe as a whole. Their calculations show that the bounce occurs at densities far below the Planck density, where we might naively expect quantum gravity effects to become important. This is because quantum geometry effects accumulate in a collapsing universe, becoming significant even at densities that are, relatively speaking, more moderate. The temperature at the bounce is finite, perhaps 10 to the power of 32 degrees Kelvin. Incredibly hot, but not infinite. The density is finite, perhaps 10 to the power of 96 kilograms per cubic meter. Unimaginably dense, but not infinite. These are extreme conditions, far beyond anything we can create or test directly. But they are comprehensible. Physics does not break down. The equations remain valid. We can calculate what happens. Moreover, the quantum bounce has testable consequences. As the universe passes through the bounce, quantum fluctuations in the geometry are imprinted on the matter and radiation. These fluctuations carry forward into the expanding phase, seeding the density variations that eventually grow into galaxies. The pattern of these fluctuations depends on the details of the bounce, and loop quantum cosmology makes specific predictions about what that pattern should look like. These predictions differ slightly from those of standard inflation. The power spectrum of fluctuations, the statistical description of how density variations depend on scale, has a different shape at very large scales. There might be additional correlations or features that standard inflation does not predict. Observations of the cosmic microwave background radiation can potentially test these predictions and distinguish between models. So far,
observations are consistent with both standard inflation and loop quantum cosmology. The differences in predictions are subtle and appear at scales where observational uncertainties are still large. But as measurements become more precise, we may be able to distinguish between these scenarios.
Future missions studying the cosmic microwave background and the large-scale structure of the universe could provide decisive tests. Beyond making predictions, the quantum bounce resolves several deep conceptual problems. It eliminates the singularity, the point where physics breaks down and our equations give meaningless answers. It extends time infinitely into the past, avoiding the paradox of time beginning from nothing. And it provides a natural initial state for the universe, a simple symmetry where the universe is transitioning from contraction to expansion. But loop quantum cosmology also raises new questions. If our universe came from a previous collapsing universe, what determined the properties of that previous universe? Was it exactly like ours, or was it different? If it was different, why did it produce our universe with these specific properties we observe? If it was the same, are we in an eternal cycle where the universe repeatedly bounces through the same states? One possibility is that information is lost at the bounce. The quantum dynamics might scramble the details of the contracting universe so that the expanding universe emerges with no memory of what came before, except for general properties like total energy and certain quantum numbers. In this case, each cycle could be different, with properties determined partly by what came before and partly by random quantum fluctuations at the bounce. Another possibility is that information is preserved but transformed. The state of the previous universe might be encoded in correlations and patterns that carry through the bounce, influencing the initial conditions of the new cycle. In this scenario, the history of the universe could extend back through many bounces, each one leaving subtle imprints that accumulate over cosmic time. There is also the question of whether the bounces continue indefinitely or eventually stop.
Some models suggest that quantum effects might gradually damp out over many cycles, eventually allowing a singularity to form after all. Others suggest that the bounces could continue forever, with the universe eternally cycling through expansions and contractions. Still others propose that the universe might eventually enter a different phase, perhaps eternal expansion like we observe today, breaking out of the cycle. Understanding these possibilities requires solving the full equations of loop quantum gravity, not just in simplified cosmological models, but in all their complexity. This is technically challenging, and many details remain unresolved. Loop quantum gravity is a work in progress, a framework that has produced remarkable insights, but is not yet complete. Critics of loop quantum gravity raise several concerns. One is that the theory has difficulty recovering standard general relativity in appropriate limits. When you zoom out from the quantum structure and average over many discrete elements, you should recover the smooth spacetime of Einstein's theory. But demonstrating this rigorously has proven difficult. Progress is being made, but the connection between the quantum and classical regimes is not yet fully understood. Another concern is that loop quantum gravity, in its current form, does not automatically include matter and radiation. It quantizes the gravitational field, but treats other fields as add-ons. This contrasts with string theory, which naturally incorporates all forces and particles in a unified framework. Loop quantum gravity theorists argue that matter fields can be included, and that doing so is conceptually straightforward, but the technical implementation remains an active area of research. There are also debates about uniqueness. Different choices in how to quantize general relativity can lead to different versions of loop quantum gravity with different predictions. Which choice is correct? Is there a unique theory of quantum gravity, or are there multiple equally valid approaches? These questions remain open. Despite these challenges, loop quantum gravity has made substantial progress in understanding quantum aspects of black holes and cosmology. It offers specific, calculable predictions about phenomena like the bounce that replaced the Big Bang singularity. And it does so while remaining conceptually conservative, avoiding the introduction of speculative new ingredients like extra dimensions or strings. The quantum bounce picture has profound philosophical implications. It suggests that the universe might be far older than 13.8 billion years. That number measures only the time since the bounce, since what we call the Big Bang. But if time extends infinitely into the past through previous contractions and bounces, then the universe has no age. It has always existed. This resolves certain philosophical paradoxes about the beginning of time. If time had a beginning, what caused that beginning? What determined the initial state? These questions disappear if time is infinite. There is no first moment to explain, no absolute beginning that requires a cause. But it replaces these questions with others. Why does the universe bounce rather than collapse to a singularity? The answer from loop quantum gravity is that quantum geometry prevents infinite compression. But why does spacetime have this quantum structure? Is it a fundamental necessity? Or could spacetime have been different, perhaps allowing singularities after all? And if the universe has undergone infinitely many bounces, why does each cycle appear to have such low entropy, such high organization and structure? The entropy problem is particularly challenging. According to the second law of thermodynamics, entropy always increases in isolated systems. Each bounce should add entropy to the universe. After infinitely many bounces, the entropy should be infinite, and the universe should be in a state of maximum disorder, a featureless thermal equilibrium with no structure. Yet we observe a universe with galaxies, stars, planets, and life, a universe with relatively low entropy and high organization. Some researchers suggest that entropy might be reset at each bounce, with quantum effects somehow erasing the memory of previous entropy increases. Others propose that the universe is not truly isolated, that it might exchange entropy with some larger structure or environment. Still others argue that we may be misunderstanding entropy in quantum cosmology, that our intuitions from thermodynamics in ordinary systems might not apply to the universe as a whole. These are open questions, areas where research is ongoing and no consensus has emerged. But they highlight that even if loop quantum gravity successfully resolves the singularity and explains the bounce, deeper mysteries remain. We may have pushed the question of cosmic origins back one step, from the singularity to the bouncing mechanism, but we have not eliminated the mystery entirely. Nevertheless, The quantum bounce represents a major conceptual advance. It shows that quantum gravity can resolve singularities in concrete, calculable ways. It demonstrates that alternatives to the standard Big Bang picture are possible and potentially testable. And it suggests that the universe might be far stranger, far older, and far more resilient than we ever imagined. The Big Bang may not have been a bang at all, but rather a bounce, a transition point in an eternal cosmic cycle. And if so, asking what came before the Big Bang has a clear answer: a contracting universe, growing denser and hotter until quantum effects reversed the collapse and initiated the expansion we observe today.
The universe that should not exist has always existed, bouncing through infinite time, eternally transforming itself from expansion to contraction and back again. The holographic principle. Imagine watching a movie in a theater. The images appear three-dimensional, full of depth and perspective, but they are actually projections from a two-dimensional film. All the information needed to create the illusion of depth is encoded on a flat surface. Now imagine something far stranger: that our entire universe, with its 3 dimensions of space extending billions of light-years in every direction, might similarly be a projection from a two-dimensional surface. That all the richness and complexity we experience, every particle, every force, every phenomenon, might be encoded on a distant boundary, like a cosmic movie screen. This is the holographic principle, one of the most radical and counterintuitive ideas in modern theoretical physics. And if it is correct, it fundamentally transforms our understanding of reality, space, time, and the question of what came before the Big Bang. It suggests that the three-dimensional universe we inhabit might be an illusion, a hologram projected from information stored on a two-dimensional surface. And that insight might provide the key to resolving the deepest mysteries of cosmic origins. The holographic principle emerged from an unexpected place: the study of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking made a series of remarkable discoveries about the thermodynamics of black holes. They found that black holes have entropy, a measure of disorder or hidden information, and that this entropy is proportional to the surface area of the black hole's event horizon, not its volume. This was puzzling. For ordinary objects, entropy is proportional to volume. A box twice as large can hold twice as many particles and has roughly twice the entropy. But for black holes, doubling the radius increases the surface area by a factor of 4 and the entropy by a factor of 4, not 8. It is as if all the information about what fell into the black hole is stored on its two-dimensional surface rather than in its three-dimensional interior. This led to a radical conjecture. Perhaps the entropy scaling with area is not just a peculiarity of black holes, but a fundamental principle of nature. Perhaps the maximum amount of information that can be stored in any region of space is determined by the area of the region's boundary, not its volume. And if information is fundamentally two-dimensional, perhaps space itself is fundamentally two-dimensional, with the third dimension emerging as a kind of holographic projection. Gerard 't Hooft and Leonard Susskind developed this idea into the holographic principle in the 1990s. They proposed that any theory of quantum gravity must satisfy a holographic bound. The number of degrees of freedom in a region of space cannot exceed the area of the region's boundary, measured in Planck units. This is not just an interesting fact about black holes. It is a constraint on the structure of space-time itself.
But the holographic principle remained somewhat abstract until Juan Maldacena made a stunning discovery in 1997. He found an explicit realization of holography in the context of string theory. Maldacena showed that a particular five-dimensional spacetime with negative curvature, called anti-de Sitter space, or ADS space, is exactly equivalent to a four-dimensional quantum field theory living on the boundary of that space. The five-dimensional theory with gravity is dual to the four-dimensional theory without gravity. They are two different mathematical descriptions of the same physical reality.
This correspondence, known as the ADS-CFT correspondence, or gauge-gravity duality, is one of the most important discoveries in theoretical physics in the last several decades. It provides a concrete example of holography, where we can calculate explicitly and verify that the duality holds. It has been tested in countless ways and has generated thousands of research papers exploring its implications. The ADS-CFT correspondence tells us something profound. Gravity in a higher dimensional space can emerge from quantum entanglement and interactions in a lower dimensional space without gravity. The geometry of spacetime, the fabric that Einstein described as warped by matter and energy, is not fundamental. It is emergent, a collective description of quantum information distributed across a holographic boundary. This has radical implications for understanding the Big Bang. If our three-dimensional space is actually a holographic projection from a two-dimensional surface, then the singularity at the Big Bang might not be physical. It might be an artifact of describing physics in the wrong variables. When we try to trace our three-dimensional universe back toward infinite density, we are pushing the holographic description beyond its regime of validity. But on the two-dimensional boundary, where the fundamental degrees of freedom live, there might be no singularity at all. Think of it this way. In the three-dimensional holographic projection, we see galaxies, stars, matter collapsing toward a singular point at the Big Bang. But this is like watching a movie where an object appears to shrink to nothing. On the film itself, the information is just being encoded differently, compressed into a smaller region, but never actually disappearing or becoming infinite. The singularity in the projection does not correspond to anything singular in the underlying description. Several researchers have explored how holography might resolve the Big Bang singularity. In some models, what appears as the Big Bang in the three-dimensional description corresponds to a phase transition or a change in state on the two-dimensional boundary. The boundary theory might have existed in some prior state, underwent a transition, and the result was what we perceive as the beginning of the universe. But from the boundary perspective, there was no beginning, just a transformation. This is similar to how water freezing into ice looks like a dramatic change, but does not represent a creation event. The molecules existed before, during, and after the transition. Only their arrangement changed. Perhaps the Big Bang is similar, appearing dramatic from our three-dimensional perspective, but representing merely a reorganization of information on the holographic boundary. Holography also provides new perspectives on the information paradox and the arrow of time. One of the deepest mysteries in cosmology is why entropy was so low at the Big Bang. The early universe was incredibly smooth and uniform, a state of very low entropy. As the universe evolved, structure formed, stars ignited, black holes appeared, and entropy increased. This growth of entropy defines the arrow of time. The reason we remember the past
but not the future. But why was entropy low to begin with? In a universe that supposedly began from a singularity where everything was compressed to infinite density, we might expect maximum entropy, complete chaos. Instead, we find order. This is sometimes called the past hypothesis, the assumption that the universe began in a low entropy state. But it is not really an explanation, more a restatement of the puzzle. Holography might help. If the Big Bang corresponds to a phase transition on the boundary, the low entropy might be natural, a consequence of how that transition occurred.
Just as water freezing starts from a high-entropy liquid state but produces a low-entropy crystalline structure under the right conditions, perhaps the holographic phase transition naturally produced a low-entropy state in the three-dimensional projection. Moreover, holography suggests that time itself might be emergent, not fundamental. On the two-dimensional boundary, the fundamental theory might be timeless, with quantum states described by their correlations rather than their evolution. Time as we experience it, with its arrow pointing from past to future, might emerge only in the three-dimensional holographic description. And if time is emergent, asking what came before time began is like asking what is north of the North Pole. The question assumes a framework that does not apply. However, there are significant challenges in applying holography to our actual universe. The ADS-CFT correspondence works for anti-de Sitter space, which has negative curvature and very different properties from our universe. Our universe has positive curvature or is flat, depending on measurements, and contains a positive cosmological constant that drives accelerated expansion. We live in what is sometimes called de Sitter space, not anti-de Sitter space. Extending holography to de Sitter space has proven extraordinarily difficult. The mathematical techniques that work so well for ADS-CFT do not carry over straightforwardly. There are deep conceptual issues about where the holographic boundary should be located in an expanding universe, what degrees of freedom live on that boundary, and how to formulate a consistent holographic description that matches observations. Some researchers are working on de Sitter holography, developing new mathematical tools and exploring different proposals for how holography might work in a universe like ours.
Others are investigating whether our universe might have properties intermediate between ADS and de Sitter space, or whether holography might apply only approximately, or in certain regions. There is also the question of what the holographic boundary actually is. In the ADS-CFT correspondence, the boundary is at spatial infinity, an infinitely distant surface where the field theory lives. But in our universe, what plays the role of this boundary? Some proposals suggest it is the cosmological horizon, the boundary of the observable universe beyond which we cannot see because light has not had time to reach us. Others suggest it might be a surface in the far future or far past, or even a space-like surface cutting through space-time. Each proposal has different implications for understanding cosmic origins. If the boundary is at late times, then information about the Big Bang might be encoded in the far future state of the universe, suggesting a kind of teleological principle, where the end determines the beginning. If the boundary is in the past, then the Big Bang might be encoded in initial boundary conditions that determine all subsequent evolution. If the boundary is spatial, then the universe might be holographic in the sense that its interior is determined by information at its edge. These ideas are speculative and far from proven, but they represent serious attempts to apply one of the deepest insights in theoretical physics to the problem of cosmic origins. And they all share a common theme. Reality might be very different from what it appears. The three-dimensional space we inhabit might be a derived concept, a convenient description that emerges at low energies but breaks down at the fundamental level. If holography is correct, then asking what came before the Big Bang might be asking the wrong question.
The Big Bang is an event in the three-dimensional holographic projection, but on the two-dimensional boundary where the fundamental degrees of freedom live, there might be no corresponding singular event. The boundary theory might have existed eternally, with the Big Bang representing merely a particular configuration or phase that the boundary passed through. Alternatively, the holographic description might reveal that the singularity is real, but represents something comprehensible when viewed in the right variables. Just as a tornado appears chaotic and dangerous from the ground, but has a simple mathematical description from above, the Big Bang singularity might appear incomprehensible in the three-dimensional description, but have a simple, well-defined structure in the holographic variables. Some physicists have even speculated about multiple layers of holography. Perhaps our three-dimensional universe is a hologram from a two-dimensional boundary, but that boundary is itself a hologram from a one-dimensional theory, which is itself a hologram from something even more abstract. The layers might continue indefinitely, with each level of description being emergent from something more fundamental. This would be the ultimate version of the idea that reality is not what it seems. Not only is the dimension of space negotiable, but there might be no fundamental number of dimensions at all. Dimensionality itself would be emergent, different at different scales and in different descriptions, with no single correct answer to how many dimensions the universe has. These ideas push the boundaries of what we can meaningfully discuss scientifically. Without experimental tests or observational evidence, we risk drifting into pure mathematics or philosophy, losing contact with physical reality. But the holographic principle is not just philosophy. It makes concrete predictions in certain contexts, and those predictions have been verified. The challenge is extending those successes to cosmology and the question of cosmic origins. What makes holography so compelling is that it emerges independently from multiple areas of theoretical physics. It appears in the study of black holes, in string theory, in quantum information theory, and in attempts to understand quantum entanglement. This convergence from different directions suggests we are onto something deep and real, even if we do not yet fully understand what it means. The holographic principle tells us that space might be emergent, not fundamental, that information is more basic than geometry, that the universe might be describable by fewer degrees of freedom than we thought, with the richness we observe emerging from quantum entanglement and correlation patterns on a lower dimensional substrate. And if this is true, then the Big Bang might not be the beginning we imagine, but rather a feature of how information is organized, a pattern in the holographic projection that appears singular only because we are viewing it from the wrong perspective. We are still learning to think holographically.
to translate our intuitions about three-dimensional space into the language of two-dimensional boundaries and emergent geometry. But as we develop these skills, we may find that the deepest questions about cosmic origins have surprisingly elegant answers. The universe that should not exist might turn out to be a necessary consequence of how information can be organized, how quantum entanglement creates geometry, and how holographic projections give rise to the illusion of space, time, and matter. The screen on which the cosmic movie plays might be more real than the movie itself. The mathematical universe. There is a question that keeps philosophers awake at night, and occasionally troubles physicists during quiet moments.
Why does mathematics work so unreasonably well in describing the universe? Why should the abstract patterns that mathematicians discover in their minds correspond so precisely to the behavior of physical reality? Einstein once remarked that the most incomprehensible thing about the universe is that it is comprehensible. But perhaps there is an even more radical answer to this puzzle. Perhaps mathematics works so well because the universe does not just obey mathematical laws. Perhaps the universe is mathematics. This is the mathematical universe hypothesis, proposed by cosmologist Max Tegmark. It is one of the most ambitious and audacious ideas in all of science, suggesting that physical reality and mathematical structure are not just similar or related, but actually identical. Every mathematical structure that can exist does exist as a physical universe somewhere in a vast multiverse of mathematical possibilities. Our universe, with its specific laws of physics and particular arrangement of matter and energy, is simply one mathematical structure among infinitely many others. If this hypothesis is correct, it transforms the question of what came before the Big Bang into a question about mathematical existence. The Big Bang would be a feature of our particular mathematical structure, but other structures might not have Big Bangs at all. Some might be timeless. Others might have different notions of causation and evolution. The multiverse would contain not just different physical universes, but different logical and mathematical frameworks, different ways that reality can be organized. To understand this idea, we need to think carefully about what we mean by mathematical existence. When a mathematician proves a theorem about prime numbers or complex spaces, is she discovering something that already existed, or is she inventing something new? Most mathematicians, if pressed, would say they are discovering. The Pythagorean theorem was true before Pythagoras proved it. It would be true even if no human had ever existed. Mathematical truths seem to transcend physical reality, existing in some abstract realm independent of space, time, and matter. Plato argued for this view over 2,000 years ago. He proposed that mathematical objects and perfect forms exist in a realm beyond the physical world, and what we perceive with our senses are merely imperfect shadows or copies of these eternal forms. A physical circle drawn on paper is never perfectly circular, but the mathematical concept of a circle exists perfectly in the realm of forms. Modern mathematicians often hold similar views, even if they do not use Platonic language. When asked whether mathematics is discovered or invented, most say discovered.
They feel they are exploring a landscape of mathematical truth that exists independently of their minds. This landscape has structure and constraints. You cannot just make up arbitrary rules and call it mathematics. Some structures are consistent and interesting. Others lead to contradictions or triviality. Tegmark takes this mathematical Platonism seriously and pushes it to its logical extreme. If mathematical structures exist in some abstract sense, and if they exist independently of physical reality, then what distinguishes them from physical reality? We might say that physical reality is the stuff that actually exists, that we can touch and measure, while mathematics is just abstract patterns. But what does it mean to exist in this sense? Consider a simulated world running on a computer, like a sophisticated video game. To the characters within that simulation, their world seems perfectly real. They experience space and time, cause and effect, objects and events. They might even develop their own physics to describe how their world works. From the outside, we know their world is just information being processed according to mathematical rules. But from the inside, there is no difference between their mathematical reality and what we call physical reality. Now imagine that you remove the computer. The mathematical structure that defined that simulated world still exists abstractly, as a set of rules and relationships that could be instantiated. Does the simulated world stop existing? Or does it continue to exist mathematically, with its inhabitants experiencing their reality just as before, even though no physical substrate is computing it? Tegmark argues that the simulated world continues to exist mathematically, and that this mathematical existence is the only kind of existence that matters. Our universe, from this perspective, is not fundamentally different from a simulated world. We are patterns within a mathematical structure, and our experience of physical reality is simply what that mathematical structure feels like from the inside. This resolves what philosophers call the hard problem of consciousness in a surprising way. We do not need to explain how mathematical structures give rise to consciousness. Instead, certain mathematical structures are conscious, in the sense that they contain subsystems that model their environment and themselves, that process information in complex ways, and that have internal experiences. Consciousness is not something added to mathematics. It is what certain sufficiently complex mathematical structures are. But if our universe is a mathematical structure, which structure is it? Tegmark suggests that our universe corresponds to the mathematical structure described by the equations of our fundamental physics. Everything we observe, every particle, every force, every interaction, is a manifestation of this structure. When physicists discover new laws or make new predictions, they are exploring the properties of our mathematical structure. This raises an intriguing possibility. Perhaps the laws of physics we observe are not contingent facts that could have been different. Perhaps they are necessary consequences of the mathematical structure we inhabit. Just as the angles of a triangle must sum to 180 degrees in Euclidean geometry, perhaps the speed of light must be 3 times 10 to the power of 8 meters per second in our mathematical structure. The constants of nature might not be arbitrary parameters that require explanation. They might be inevitable features of a particular mathematical framework. But then, why this mathematical structure and not another? Why do we find ourselves in a universe described by quantum field theory and general relativity, rather than some other mathematical framework? This is where Tegmark makes his most radical move. He proposes that all consistent mathematical structures exist. There is not just one universe, but infinitely many, each corresponding to a different mathematical structure. This is the level 4 multiverse, the ultimate ensemble that contains every possible mathematical reality. In this view, asking why our universe exists is like asking why the number 7 exists. It exists because mathematical existence requires no physical instantiation or external cause. It simply is. And we observe this particular universe because we are part of this particular mathematical structure. We could not observe any universe whose structure does not allow for observers to exist. This anthropic reasoning is similar to what we encountered with eternal inflation. But here, it is even more extreme. The level 4 multiverse contains not just universes with different physical constants, but universes with completely different mathematical structures. Some might have different numbers of spatial dimensions, or multiple time dimensions, or no notion of space and time at all. Some might operate according to classical logic, others according to quantum logic, or fuzzy logic, or modal logic. The diversity is unlimited, encompassing every consistent mathematical possibility. Critics raise several objections to the mathematical universe hypothesis. One is that it seems unfalsifiable. If every mathematical structure exists somewhere, then no observation can contradict the hypothesis. We will always find ourselves observing something consistent with some mathematical structure, because that is a tautology. How can we test a theory that predicts everything? Tegmark responds that the hypothesis does make predictions. It predicts that our universe should be describable by relatively simple mathematics with no arbitrary parameters. Complicated, fine-tuned structures are vastly outnumbered in the space of mathematical possibilities by simpler, more generic structures. So we should expect to find ourselves in a universe with elegant, economical laws. The fact that physicists have been successful in finding such laws, that the Standard Model and general relativity can be written down concisely, supports the hypothesis. Moreover, if further observations reveal inexplicable fine-tuning or arbitrary complexity in the laws of physics, that would count against the mathematical universe hypothesis. If we discover that the electron mass is fine-tuned to 100 decimal places for no apparent reason, that would suggest our universe is not a natural mathematical structure, but rather something designed or selected by non-mathematical criteria. Another objection is that not all mathematical structures are consistent or well-defined. Some lead to paradoxes, like Russell's paradox or Gödel's incompleteness theorems. If a mathematical structure contains contradictions, can it exist as a universe? What would it even mean for an inconsistent structure to exist? Tegmark acknowledges this challenge, but suggests that only consistent mathematical structures correspond to actual universes. Inconsistent structures do not exist in any meaningful sense, even mathematically. This introduces a constraint on the multiverse.
only logically consistent structures are realized. But determining which structures are consistent is itself a deep mathematical problem, and there is no algorithm for deciding consistency in general. So the boundary of the Level 4 multiverse remains somewhat fuzzy and philosophy-laden. There is also a disturbing consequence related to measure and probability. In an infinite multiverse containing all mathematical structures, how do we calculate probabilities? Some structures will contain infinitely many observers, others only finitely many. How do we weight them when computing what a typical observer should expect to see? This is another version of the measure problem, and it remains unsolved. Despite these challenges, the mathematical universe hypothesis offers a compelling answer to the question of cosmic origins. If the universe is fundamentally mathematical, then it requires no cause or explanation beyond the existence of mathematics itself. Mathematics exists necessarily, as a matter of logical fact. So universes corresponding to mathematical structures also exist necessarily. The Big Bang is not a moment of creation, but rather the beginning of time within our particular mathematical structure. Other structures might have different beginnings or no beginning at all. This perspective also sheds light on the mystery of why the laws of physics appear fine-tuned for life. In a single universe, fine-tuning seems miraculous and demands explanation. But in the Level 4 multiverse, fine-tuning is expected. Most mathematical structures will not support complexity or life, but some will, and observers will necessarily find themselves in those rare structures. There is no deeper reason why our universe has the properties it does. We simply could not observe any universe where observers cannot exist. Some physicists find this reasoning unsatisfying. It seems to give up on finding a unique explanation for our universe, replacing necessity with anthropic selection. But others see it as the ultimate explanation, showing that existence itself requires no cause, because mathematical structures exist by logical necessity. The mathematical universe hypothesis also connects to the simulation hypothesis. If our universe is a mathematical structure, and if advanced civilizations can simulate universes by instantiating mathematical structures on computers, then most observers might actually be in simulations rather than base reality. This is because simulations can be nested arbitrarily deep. A civilization might create many simulations, each of which contains civilizations that create their own simulations, and so on. The number of simulated observers could vastly exceed the number of base-level observers. But in Tegmark's framework, this distinction might be meaningless. A mathematical structure does not care whether it is being computed on a physical computer or whether it exists purely abstractly. The experience of observers within the structure is the same either way. So asking whether we are in a simulation is like asking whether our mathematical structure is being thought about by some external intelligence. It might be true, but it makes no difference to our experience or the laws that govern our reality. This leads to a vertiginous conclusion. We might be mathematical patterns that exist necessarily, inhabiting a structure that requires no physical instantiation, experiencing a reality that feels tangible and concrete, but is ultimately nothing more than relationships and equations. Physical matter would be revealed as a useful fiction, a way of describing certain patterns in the mathematical structure. What we call particles and forces would be features of the equations,
not things that exist independently. Yet, from another perspective, this makes physical reality more solid, not less.
If the universe is mathematics, then it exists with the same necessity as mathematical truth. It cannot not exist. The question of why there is something rather than nothing is answered. There must be something because mathematical structures exist necessarily. And physical reality is simply what certain mathematical structures are. The mathematical universe hypothesis transforms cosmology from physics into metamathematics. Understanding cosmic origins becomes a question about the structure of mathematical possibility space, about which structures are consistent, about anthropic selection effects in an infinite ensemble, about measure problems in infinite sets. These are profound questions at the intersection of physics, mathematics, logic, and philosophy. If Tegmark is right, then before the Big Bang there was no time in our mathematical structure, but there were infinitely many other mathematical structures, some with their own notions of time and causation, others timeless and eternal. The multiverse is not physical but mathematical, and it contains every possible way that reality can be organized according to consistent rules. We are explorers in this mathematical landscape, discovering through physics and observation which structure we inhabit, what its properties are, why it allows for complexity and consciousness. And ultimately, we are the universe understanding itself. Mathematical patterns achieving self-awareness and contemplating their own existence. The universe is mathematics, and mathematics is the only thing that could not exist. The simulation hypothesis. In the year 1999, a film called The Matrix presented audiences with a disturbing premise.
What if the world we experience is not real, but rather a computer simulation, a virtual reality indistinguishable from actual reality? What if we are not biological beings living on Earth, but rather simulated minds running on alien hardware? The movie was science fiction, but the question it posed was genuine. How would you know if you were in a simulation? And more importantly, could you ever prove that you are not? This question has haunted philosophers for centuries in various forms. Descartes worried that an evil demon might be deceiving him about the nature of reality. Buddhist philosophers suggested that the material world is Maya, illusion, a kind of dream from which enlightenment provides awakening. But in the 21st century, with the explosive growth of computing power and virtual reality technology, the simulation hypothesis has taken on new urgency and scientific respectability. The modern version of the argument was crystallized by philosopher Nick Bostrom in a paper published in 2003. Bostrom proposed what he called the simulation argument, which goes roughly as follows. Assume that technological civilizations can continue advancing without destroying themselves. Eventually, such civilizations would possess computing power sufficient to run detailed simulations of their ancestors, complete with simulated consciousness and subjective experience. These ancestor simulations would be extraordinarily valuable for historical research, entertainment, education, and countless other purposes. A single advanced civilization might run billions or trillions of such simulations. Now comes the key insight. If this is possible, and if it actually happens, then most conscious beings would be simulated rather than biological. For every civilization at the base level of reality, there could be countless simulations, each containing billions of conscious individuals who believe they are at the base level. Simple probability suggests that you are far more likely to be one of the simulated minds than one of the rare base-level minds. This leads to Bostrom's trilemma. At least one of the following three statements must be true. First, almost all civilizations at our stage of development go extinct before reaching the technological capability to run ancestor simulations. Second, civilizations that reach that capability choose not to run such simulations, perhaps for ethical reasons or lack of interest. Third, we are almost certainly living in a simulation. The argument is probabilistic, not definitive. It does not prove we are in a simulation, but it suggests that unless there are barriers we do not currently foresee, simulated realities vastly outnumber base reality, and we should take seriously the possibility that we inhabit one of them. If we are in a simulation, this has profound implications for the question of what came before the Big Bang. The Big Bang would not be the beginning of reality, but merely the beginning of our simulation. Before our simulated universe started running, there was the base reality, where the simulation is being executed. And in that base reality, there might be a very different history, different laws of physics, perhaps no Big Bang at all. The simulators could have started our simulation at any point. They might have begun it 13.8 billion years ago in simulated time and let it run forward. Or they might have started it yesterday with all our memories of the past preloaded as initial conditions. We would have no way to tell the difference. The past, beyond the start of the simulation, would not exist except as data in our simulated memories. This means that even if we observe evidence for the Big Bang, cosmic microwave background radiation, nucleosynthesis ratios, all of it, we cannot conclude that those events actually happened. They might be simulated evidence for a simulated history. The universe might have been created last Thursday with everything already in place, including fossils, light from distant galaxies, and your memories of breakfast last week. Philosophers call this last Thursdayism, and it is technically unfalsifiable. No evidence can prove that the past actually happened, rather than being an elaborate fabrication. This is deeply unsettling because it undermines the entire project of cosmology. If we cannot trust that the past was real, how can we hope to understand cosmic origins? One response is to apply Occam's razor. The simplest explanation for our observations is that the past actually happened as our observations suggest. Proposing that we are in a simulation started last Thursday is a more complex hypothesis requiring additional assumptions. Unless we have positive evidence for the simulation, we should prefer the straightforward interpretation. But do we have positive evidence? Some researchers have suggested that simulations might leave detectable signatures, glitches in the matrix that could reveal the artificial nature of our reality. If our universe is being computed on a discrete grid, for instance, there might be a minimum length scale below which space does not exist. This would manifest as a cutoff in the energy spectrum of cosmic rays, or subtle anomalies in particle physics. Physicists have looked for such signatures and found nothing conclusive so far. The universe appears continuous down to the scales we can probe. But this does not rule out simulations. The simulators might be using analog computation, or computation on scales far smaller than we can access, or techniques we cannot even imagine. A sufficiently advanced simulation would be indistinguishable from base reality by design. There is also a subtle philosophical point. Even if we found evidence that our universe is computed on a discrete grid, this would not prove we are in a simulation. It might simply mean that space is fundamentally discrete, as loop quantum gravity suggests. Conversely, the absence of such evidence does not prove we are not in a simulation. The simulators might have perfect fidelity. Some thinkers have proposed that we could influence the simulators through our behavior. If we do things that make our simulation more interesting or valuable to the simulators, they might be more likely to keep it running rather than shutting it down. This leads to bizarre recommendations about how to act if you believe you are in a simulation. Make yourself entertaining. Be historically significant. Do unexpected things that would be worth simulating. But this reasoning is deeply speculative and perhaps incoherent. We have no idea what the simulators value or whether they even exist. Moreover, if we are in a simulation designed to study how humans behave in natural conditions, then trying to game the system by acting for the benefit of simulators would defeat the purpose of the simulation. The simulators might terminate simulations that become aware of their nature and start behaving differently as a result. Others have suggested that simulations might have resource constraints that could manifest as observable phenomena. If computation is expensive, the simulators might only compute high-resolution details in regions being observed, like how video games render only what is on screen. This would predict that quantum mechanics, with its observer-dependent collapse of wave functions, is actually an optimization technique in the simulation. The universe exists in a low-resolution probabilistic state until observation forces high-resolution rendering. This is a fascinating parallel between quantum mechanics and simulation theory, but it does not constitute evidence for simulation. Quantum mechanics can be understood without reference to simulation as a fundamental feature of nature. The fact that it could also be explained as a computational optimization is interesting, but does not favor one interpretation over the other. The simulation hypothesis also raises questions about consciousness. If we are simulated, are we truly conscious or merely philosophical zombies, programs that behave as if conscious without actually having subjective experiences? This depends on your theory of consciousness. If consciousness is substrate independent, if it can arise in any sufficiently complex information processing system, regardless of whether that system is biological neurons or silicon chips or exotic computronium, then simulated minds could be just as conscious as biological minds. Most philosophers and neuroscientists lean towards substrate independence. There is no magic in carbon chemistry that makes consciousness possible. What matters is the patterns of information processing, the functional relationships between components, not the specific material implementation. If this is correct, then simulated beings would be conscious, their experiences just as real as ours, even though their reality is implemented on hardware in some other universe. This raises ethical concerns about creating simulations. If simulated beings are conscious, then running a simulation involves bringing conscious entities into existence, entities that can suffer, that have preferences and desires, that have moral status. Are we obligated to treat simulated beings ethically? If we create a simulation containing suffering, are we responsible for that suffering? Some ethicists argue that ancestor simulations, simulations of historical periods including war, disease, and death, would be deeply immoral to run. Others suggest that advanced civilizations would recognize these ethical issues and refrain from running realistic simulations with suffering. This could explain the second horn of Bostrom's trilemma.
Perhaps advanced civilizations have the technology to run simulations, but choose not to for ethical reasons. But this assumes that all advanced civilizations would converge on similar ethical principles. It seems more likely that different civilizations would make different choices. Some might run simulations, others might not. And if even a tiny fraction of advanced civilizations run simulations, the simulation argument still goes through. The number of simulated minds would vastly exceed base-level minds. There is another disturbing possibility. If we are in a simulation, the simulation itself might be running inside another simulation, which is running inside yet another simulation, nested like Russian dolls. There might be a vast hierarchy of simulated realities, with each level simulating countless instances of the level below. Most conscious beings would be not just simulated, but multiply simulated, existing many layers removed from base reality. At some point in this hierarchy, there must be a base level, a reality that is not itself simulated. Or must there be? Some have speculated about closed time-like loops where the simulation creates the simulator, circular causation that eliminates the need for a base level altogether. This leads to dizzying metaphysical puzzles that might not even be coherent. From the perspective of understanding what came before the Big Bang, the simulation hypothesis offers a clear answer. The simulator's reality came before. Our Big Bang is an event within a simulation running in some other universe. That universe might have its own Big Bang, or it might be eternal, or it might have some completely different structure. We cannot know without communicating with the simulators, which might be impossible. Some researchers have half-seriously proposed ways to send messages to the simulators. If we detect glitches or anomalies in physics, we might interpret them as messages.
Or we might try to create patterns in our behavior or in the structure we build that would be noticeable to anyone observing the simulation from outside. This is highly speculative, bordering on religious thinking about communicating with higher beings who created our reality. The simulation hypothesis shares many features with religious worldviews. The simulators play the role of gods or demiurges, creators of our reality who exist outside it. The beginning of the simulation is like creation. The possibility of the simulation ending is like escaping apocalypse. Communication with simulators parallels prayer or revelation. Some have even suggested that religious experiences might be interventions by the simulators, deliberate manipulations of the simulation for reasons we cannot fathom. But unlike traditional religion, the simulation hypothesis makes no moral claims and provides no meaning or purpose. The simulators might be indifferent to us, running the simulation for reasons that have nothing to do with our well-being. They might be students doing a homework assignment, or artists creating entertainment, or scientists studying emergent complexity. We have no reason to think they care about us at all. This raises existential questions. If we are in a simulation, does life have meaning? Do our choices matter? On one level, the answer is the same whether we are in a simulation or not. From our perspective, our experiences are real, our relationships meaningful, our suffering genuine. The existence of a higher level of reality does not negate our reality, any more than learning about quarks and quantum fields negates the reality of tables and chairs. But on another level, the simulation hypothesis is destabilizing. It suggests that everything we think we know might be contingent on the choices of the simulators. They could change the laws of physics insert or remove objects, manipulate our memories, or terminate the simulation entirely.
We have no control and no recourse. This is a kind of cosmic helplessness that some find profoundly troubling. Interestingly, the simulation hypothesis is testable in principle, though perhaps not in practice. If we developed the technology to run our own high-fidelity simulations of universes with conscious beings, this would provide existence proof that such simulations are possible. And if they are possible for us, they are probably possible for civilizations more advanced than ours. The more advanced our own simulations become, the more plausible it is that we ourselves are simulated. Conversely, if we discover fundamental barriers to running such simulations, physical or computational limits that prevent conscious beings from being simulated, this would weaken the simulation argument. If simulations are impossible, we cannot be in one. So research into the nature of consciousness and the requirements for artificial consciousness has bearing on the simulation question. Some physicists have suggested that we should be skeptical of the simulation hypothesis on anthropic grounds. If most conscious beings are simulated, and if simulations can have different laws of physics than base reality, then we should expect to observe simple, easily simulatable laws. But our universe appears to require quantum mechanics and general relativity, complex mathematics that is computationally intensive to simulate accurately. This might suggest we are more likely to be in base reality than in a simulation. But this argument assumes that simulators would choose simple laws. Perhaps they specifically want to simulate complex physics to study emergent phenomena. Or perhaps the laws in base reality are even more complex, making our universe relatively simple by comparison. Without knowing the distribution of simulation purposes and methods, we cannot make strong anthropic inferences. The simulation hypothesis remains controversial and speculative. Most physicists do not seriously entertain it when doing research, treating it as a philosophical curiosity rather than a scientific hypothesis. But a growing minority takes it seriously, and the argument continues to generate discussion and debate. If the simulation hypothesis is correct, then the question of what came before the Big Bang has a surprising answer. Before our universe, there was the simulator's universe, with its own history, its own evolution, its own structure. Our origins are not cosmological, but computational. We were programmed into existence by intelligences in another reality, and our entire history is the execution of that program. The universe that should not exist might simply be a universe that was simulated into existence, as real to us as any universe could be, but ultimately dependent on decisions made in a reality forever beyond our reach.